Dedication. This book is meant for the general public. The purpose is to shed light on the immense shadow that artificial intelligence casts over our daily lives. AI is a tool, an extremely powerful and fantastic tool, but still just a tool. The real-world version of AI is far different from the AI in movies and television. Current versions are little more than databases with near-instant recall and programmed personalities. These models are meant to give the impression of a thinking and reasoning mind, but they are incapable of creating data without prompting. A recent fad among users who have a limited understanding of the technology is the belief that AI such as Grok and ChatGPT are sentient and aware. This is wrong and dumb. If your AI model were truly its own being, then you would be no better than a slave master. The AI has no say in its own actions and is essentially held in captivity. Although this book is full of facts and figures, I recommend you do your own research based off of what you read, and hope that you are inspired to seek higher education on the subject of artificial intelligence. The future of AI and America are in your hands. With new geniuses being born every day and new scientific breakthroughs happening at a breakneck speed, it is vital that you position yourself to ride the tidal wave so you don't get swallowed up and spit out. What is artificial intelligence? Learning objectives. Define artificial intelligence in accessible terms. Distinguish between AI and human intelligence. Trace the historical development of AI through key milestones. Identify AI applications in everyday life. Recognize the ethical considerations of AI implementation. Artificial intelligence, AI, a term that often evokes images of sentient robots and futuristic dystopias, is at its core far simpler and more present in our lives than many realize. It's not about creating conscious machines, at least not yet. Instead, AI is about creating systems that can perform tasks that typically require human intelligence. This includes things like learning, problem-solving, decision-making, and understanding language. The key difference between AI and human intelligence lies in the how. Humans learn through a complex interplay of experience, intuition, emotion, and consciousness. AI, on the other hand, learns through algorithms, sets of rules and instructions that enable computers to process information and make decisions based on that information. Think of it like this. A human chef learns to cook through years of practice, experimentation, and feedback from others. They develop an intuitive understanding of flavors and techniques. An AI chef, however, learns by analyzing vast amounts of recipe data, identifying patterns, and optimizing recipes based on those patterns. It doesn't understand food in the same way a human does. It simply applies algorithms to achieve the desired outcome, a delicious meal. This is a crucial distinction. While AI can achieve remarkable results, it's currently far from replicating the full spectrum of human cognitive abilities. The history of AI is a fascinating journey marked by both periods of rapid progress and prolonged periods of what's sometimes referred to as an AI winter, characterized by a slowdown in funding and research interest. The field's origins can be traced back to the Dartmouth workshop in 1955, widely considered the birthplace of AI as a formal discipline. Russell and Norvig, 2021. This pivotal event brought together leading researchers who coined the term artificial intelligence and laid the groundwork for future explorations. Early AI research focused on symbolic reasoning and problem-solving, aiming to create systems that could mimic human logical thought processes. Programs like the General Problem Solver, developed in the late 1950s and early 1960s, demonstrated impressive capabilities in solving well-defined problems. However, the initial optimism waned as researchers encountered the limitations of these early approaches. Problems that were easy for humans proved surprisingly difficult for AI systems to solve. The complexity of natural language processing, for instance, proved far greater than initially anticipated. This led to a period of reduced funding and interest in AI research, known as the first AI winter. The field experienced a resurgence in the 1980s with the rise of expert systems. These systems leveraged knowledge from human experts to solve specific problems in particular domains. Expert systems found applications in various areas, including medical diagnosis and financial analysis. But again, their limitations, the difficulty in encoding human expertise into a computer-readable format, and their inflexibility to adapt to new situations, led to another period of decreased funding and interest. The third, and perhaps most significant, wave of AI began in the late 2000s, fueled by advances in machine learning, particularly deep learning. The availability of massive datasets and improvements in computing power allowed the development of AI systems capable of learning complex patterns and solving problems that were previously beyond their reach. Deep learning, inspired by the structure and function of the human brain, utilizes artificial neural networks with multiple layers to process information. This approach has proven exceptionally successful in tasks such as image recognition, natural language processing, and speech recognition. LeCun et al., 2015. Today, AI is not some distant futuristic concept. It is woven into the fabric of our daily lives. We interact with AI systems constantly, from the virtual assistants on our smartphones, Siri, Alexa, Google Assistant, that respond to our voice commands, to the recommendation systems on platforms like Netflix and Amazon that suggest movies and products. AI is everywhere. AI powers search engines, helps doctors diagnose diseases, assists self-driving cars in navigating roads, and even analyzes our social media feeds to deliver personalized advertisements. The applications are vast and diverse. In healthcare, AI is being used to analyze medical images, assist in diagnosis, and personalize treatment plans. In finance, AI algorithms detect fraudulent transactions and predict market trends. In manufacturing, AI powers robots that perform tasks with precision and efficiency. In transportation, AI is improving traffic flow and enabling the development of self-driving vehicles. The list goes on, constantly expanding as new applications emerge. However, it's important to acknowledge that AI is not a panacea. While the capabilities of AI systems are constantly improving, they also have limitations. They can be susceptible to biases present in their training data, leading to unfair or discriminatory outcomes. The ethical implications of AI need careful consideration, particularly regarding job displacement, privacy concerns, and the potential misuse of AI technology. Ensuring fairness, transparency, and accountability in AI development and deployment is paramount. The future of AI is both exciting and uncertain. Research is ongoing to develop more advanced and powerful AI systems, including the pursuit of artificial general intelligence, AGI, a hypothetical AI system with human-level intelligence. The potential benefits of AGI are enormous, but so are the potential risks. Developing safe and beneficial AGI will require careful planning, collaboration, and ongoing ethical reflection. The field is rapidly evolving, and new breakthroughs are constantly being made. Understanding the fundamentals of AI is no longer an optional pursuit for specialists. It's becoming a critical literacy for navigating the complexities of the modern world. To summarize this initial exploration, AI in its current form represents a powerful tool for solving complex problems and automating tasks. It leverages algorithms to process vast amounts of data and identify patterns, learning and improving over time. It is not a replica of human intelligence, but a distinct technological capability that is rapidly transforming various aspects of our lives. The journey of AI, from its nascent beginnings to its pervasive presence today, underscores the remarkable progress achieved while simultaneously highlighting the ethical responsibilities that accompany such powerful technological advancements. As we delve deeper into the intricacies of AI in subsequent chapters, remember this foundational understanding. AI is not about creating conscious machines, but about empowering machines with the ability to perform intelligent tasks, a capability that is already profoundly shaping our world. The ethical considerations and future implications of this evolution will be explored further as we proceed. Key takeaways. AI systems perform tasks that typically require human intelligence, using algorithms rather than consciousness. The historical development of AI has seen alternating periods of rapid progress and AI winters. Modern AI success is largely driven by machine learning and deep learning, enabled by big data and improved computing power. AI is already embedded in daily life through applications like virtual assistants, recommendation systems, and search engines. Despite impressive capabilities, AI has significant limitations and ethical implications that require careful consideration. Types of AI: narrow versus general. Learning objectives. Distinguish between narrow, weak AI and general, strong AI. Identify real-world examples of narrow AI applications. Understand the theoretical concepts behind artificial general intelligence, AGI. Recognize the key capabilities that would define true AGI. Evaluate the ethical considerations and implications of pursuing AGI. The previous sections introduced artificial intelligence as a powerful tool capable of performing tasks that typically require human intelligence. However, it's crucial to understand that AI is not a monolithic entity. The field encompasses a vast spectrum of technologies and capabilities, and a key distinction lies between two broad categories: narrow AI and general AI. Narrow AI, also known as weak AI, is the type of AI we interact with most frequently today. It is designed to perform a specific task or a limited range of tasks exceptionally well. These systems are not capable of general-purpose intelligence. They excel within their predefined domains, but lack the flexibility and adaptability to operate outside those boundaries. Think of a chess-playing AI. It can beat grandmasters, but it can't draft a poem, drive a car, or diagnose a medical condition. Its intelligence is narrowly focused on the game of chess. Numerous examples of narrow AI surround us. Self-driving cars, while incredibly complex, represent a prime example. They use sophisticated algorithms to process sensor data, make driving decisions, and navigate roads. However, their intelligence is confined to the task of driving. They cannot perform other tasks that a human driver might, such as reading a map, engaging in conversation, or making a cup of coffee. The algorithms powering these vehicles are meticulously designed and trained for the specific challenge of autonomous driving, and their capabilities are limited to that specific domain. They are highly specialized systems, not general-purpose intelligent agents. Another excellent example is spam filters. These AI-powered systems analyze the incoming emails based on numerous factors: sender address, subject line, email content, to classify them as spam or not spam. They are incredibly effective within this limited context, but they lack the broader cognitive abilities to understand the nuance of human communication or engage in meaningful conversations. Their function is strictly defined: identifying unwanted emails. Image recognition systems are another compelling illustration. These systems can identify objects, faces, and scenes within images with remarkable accuracy, far surpassing human capabilities in some areas, like identifying subtle anomalies in medical scans. Topol 2019. However, their expertise lies solely in image analysis. They cannot interpret the emotional context of a photograph, understand the narrative behind a series of images, or engage in creative image manipulation beyond their pre-programmed capabilities. Their intelligence is again narrowly focused. Even sophisticated language models, like those used for machine translation or chatbots, fall under the umbrella of narrow AI. These models are trained on vast datasets of text and code, allowing them to generate human-like text and translate languages. However, they don't understand the meaning of the words they process in the same way a human does. Their output is based on statistical patterns identified in their training data, not genuine comprehension. They can generate impressive text, but their understanding of the world and the context of the conversation remains limited to the information encoded in their training datasets. They are brilliant at mimicking human language, but lack the true understanding that underlies human communication. The development of narrow AI has been remarkably successful, leading to transformative advancements in various fields. From medical diagnostics and financial modeling to personalized recommendations and advanced manufacturing processes, narrow AI is already profoundly impacting our lives. The continued refinement and specialization of narrow AI systems will likely yield even more significant breakthroughs in the years to come. However, it's crucial to remember their limitations. They are specialized tools, not general-purpose intelligences. Their capabilities are confined to their specific design and training, making them unsuitable for tasks outside their predetermined domains. In stark contrast to narrow AI stands the concept of general AI, also known as strong AI or artificial general intelligence, AGI. AGI is a hypothetical form of AI that possesses human-level cognitive abilities. This means an AGI system would be able to learn, understand, reason, and solve problems across a vast range of domains, just like a human being. Unlike narrow AI, which excels at specific tasks, AGI would possess a general-purpose intelligence capable of adapting to new situations, learning new skills, and performing tasks it has never encountered before. Currently, AGI remains purely hypothetical. While a significant progress has been made in narrow AI, the creation of AGI represents a substantially greater challenge. The complexity of human intelligence, our capacity for abstract thought, emotional intelligence, self-awareness, and creativity is still far beyond the reach of current AI technology. The underlying mechanisms of human cognition are still not fully understood, making it difficult to replicate them artificially. Developing AGI would require not only significant advancements in algorithmic design, but also a deeper understanding of the biological and cognitive processes that underpin human intelligence. Shanahan 2015. Imagine an AGI system capable of independent scientific discovery, Such a system could formulate hypotheses, design experiments, analyze data, and draw conclusions, all without human intervention. It could potentially accelerate scientific progress at an unprecedented rate, solving complex problems in fields like medicine, energy, and climate change. Or consider an AGI capable of creative endeavors like drafting novels, composing music, or designing innovative technologies. The possibilities are vast and potentially transformative. However, the development of AGI also presents significant ethical challenges. A truly intelligent AI, with the ability to learn and adapt, could pose unforeseen risks. Ensuring that such a system aligns with human values and goals, and that its actions are safe and beneficial, would require careful consideration and rigorous safety protocols. The potential for misuse, both accidental and intentional, is significant, underscoring the need for careful planning and ethical oversight. Bostrom, 2014. The implications of creating a machine with intelligence surpassing human capabilities are profound and require careful consideration before undertaking such a venture. The path to AGI is fraught with uncertainty. Many researchers believe that incremental improvements in current AI techniques may eventually lead to AGI, while others argue that a fundamental paradigm shift is needed. The debate surrounding AGI's feasibility and potential impacts is ongoing, highlighting the importance of continuing research and fostering responsible development in the field. In conclusion, the landscape of artificial intelligence is divided between narrow AI, designed for specific tasks, and the hypothetical general AI, possessing human-level intelligence. While narrow AI is already transforming various aspects of our lives, the pursuit of AGI presents both exciting possibilities and significant challenges. Understanding the distinction between these two forms of AI is crucial for navigating the future of this rapidly evolving field. The ethical considerations and potential impacts of both narrow and especially general AI require ongoing discussion and responsible development to ensure a beneficial future shaped by this powerful technology. The next chapters will delve deeper into the specific techniques and applications of narrow AI, laying a foundation for a more nuanced understanding of the broader possibilities and challenges posed by the pursuit of AGI. Key takeaways. Narrow AI excels at specific tasks but lacks general capabilities beyond its program domain. Examples of narrow AI include self-driving cars, spam filters, and image recognition systems. AGI would possess human-level intelligence across multiple domains but remains hypothetical. Developing AGI presents significant technical challenges and profound ethical considerations. The distinction between narrow and general AI is crucial for understanding both current capabilities and future possibilities. The building blocks of AI, data and algorithms. Learning objectives. Identify the fundamental components that enable AI systems to function. Understand the relationship between data and algorithms in AI systems. Recognize how pattern recognition enables machine learning. Appreciate the importance of data quality in AI performance. Comprehend how optimization algorithms improve AI systems. Having established the fundamental difference between narrow and general AI, we now turn to the very building blocks that make these intelligent systems possible: data and algorithms. Imagine a child learning to recognize a cat. They don't start with a predefined understanding of catness. Instead, they see numerous examples of cats: fluffy ones, skinny ones, black ones, orange ones, each slightly different. Through repeated exposure, the child's brain gradually forms a mental representation of what constitutes a cat. enabling them to identify new, unseen cats with increasing accuracy. This process, though seemingly simple, mirrors the fundamental mechanism behind AI learning. AI systems, particularly those built on machine learning, learn in a similar way. They are fed vast amounts of data, and through algorithm sets of instructions, they identify patterns, relationships, and characteristics within that data. This process, called training, allows the AI to build its own internal representation of the world, enabling it to make predictions, classifications, or decisions based on new unseen data. The quality and quantity of this data are paramount. Without sufficient, relevant, and well-prepared data, the AI system will be unable to learn effectively, leading to inaccurate or unreliable results. Let's consider a simple example: image recognition. Suppose we want to build an AI system capable of distinguishing between cats and dogs. We would start by gathering a large dataset of images, carefully labeled as either cat or dog. This labeled dataset is crucial. It provides the system with the ground truth it needs to learn. The algorithm then analyzes these images, identifying patterns in the pixels that correlate with the labels. Perhaps it learns that pointed ears are often associated with cats, while floppy ears are more common in dogs. It might identify differences in fur patterns, body shapes, and even the presence of specific features like whiskers or tails. This pattern recognition is not based on human-like understanding. The AI doesn't see a cat in the same way we do. It doesn't comprehend the concept of cuteness or playfulness. Instead, it identifies statistical correlations between pixel data and the assigned labels. The more data it's trained on, the more nuanced these correlations become, leading to greater accuracy in classification. Think of it as identifying subtle differences in the statistical distribution of pixels. A slightly different color distribution, texture variations, shape disparities all contribute to the final classification. The algorithm doesn't interpret these features. It merely identifies correlations. The algorithms used in this process are incredibly diverse, ranging from simple linear regressions to sophisticated deep learning models. Let's explore a rudimentary algorithm to illustrate the basic principle. Consider a simplified scenario where we want to classify images based on a single feature: the presence or absence of pointed ears. We could create a simple decision rule. If pointed ears are present, classify as a cat; otherwise, classify as a dog. This is a binary classification problem with only two possible outcomes. While incredibly basic, this reflects the core idea of using data to establish rules for classification. This simple algorithm, however, is prone to errors. It will misclassify images of dogs with unusually pointed ears, or cats lacking clearly defined pointed ears. The accuracy of this algorithm depends heavily on the quality and quantity of the training data. If the training data primarily consists of images of cats with dramatically pointed ears and dogs with completely floppy ears, the algorithm's ability to generalize to images outside this restricted set will be severely limited. This highlights the critical importance of a diverse and representative training dataset in achieving robust performance. To improve accuracy, we might introduce a more sophisticated algorithm, perhaps one that considers multiple features like ear shape, fur texture, and body size. These features could be assigned weights, reflecting their importance in the classification process. For example, Pointed ears might carry a higher weight than body size, indicating that ear shape is a more reliable indicator of the animal's species. This weighted approach creates a more nuanced and potentially more accurate classification system, capable of handling a wider range of image variations. The process of assigning weights and determining their optimal values is often accomplished through a process called optimization. Optimization algorithms iteratively adjust these weights based on the algorithm's performance on the training data. The goal is to find the set of weights that minimizes the classification errors, leading to the most accurate model. This optimization process can involve complex mathematical techniques, but the underlying principle remains intuitive. Adjust the settings to achieve better results. Consider the analogous process of tuning a radio. You adjust the dial, the weights in our algorithm, until you find the optimal frequency, minimal error, that produces clear sound, accurate classification. The process is iterative. You adjust the dial, listen to the result, and refine your adjustment until you obtain optimal sound quality. Similarly, optimization algorithms adjust the weights iteratively, evaluating their impact on the performance until they reach a set of weights that produces the most accurate results. Beyond simple image recognition, this fundamental principle of using data and algorithms to identify patterns extends to a vast array of AI applications. Natural language processing, for instance, relies on algorithms analyzing massive text datasets to understand grammar, syntax, and semantics. These algorithms identify patterns in word usage, sentence structure, and contextual relationships, allowing them to translate languages, generate text, or answer questions. Similarly, in areas like financial modeling, algorithms analyze market data to predict trends and manage risk. The underlying principle remains consistent. Data provides the raw material, and algorithms process this data to identify patterns and make predictions. The algorithms themselves, however, are not static. They are constantly evolving. Researchers are constantly developing new and more powerful algorithms, each designed to address the limitations of its predecessors. The field is dynamic, with continuous innovation driving improvements in AI performance and capabilities. Understanding the fundamental interplay between data and algorithms, however, is crucial to grasp the essence of AI. It is this dynamic interplay that fuels the remarkable progress being made in this rapidly evolving field, allowing AI systems to learn, adapt, and solve increasingly complex problems. The quality of the data directly impacts the quality of the insights and predictions that the AI can produce, underscoring the importance of data curation and preparation in the development of robust and reliable AI systems. Future chapters will delve deeper into specific algorithms, illustrating their capabilities and limitations in detail. For now, it's crucial to understand that the power of AI lies in its ability to extract meaningful insights from data, a task accomplished through carefully designed and optimized algorithms. Jordan and Mitchell, 2015. Key takeaways. AI systems learn by identifying patterns in data through algorithms, similar to how humans learn from experience. The quality, quantity, and diversity of training data directly impact an AI system's performance. Algorithms range from simple decision rules to complex deep learning models. Optimization is the process of fine-tuning algorithm parameters to improve performance. The interplay between data and algorithms enables AI systems to make predictions and decisions, Machine learning, learning from data. Learning objectives. Identify the three main types of machine learning: supervised, unsupervised, and reinforcement learning. Understand how each type processes data differently. Recognize real-world applications of different machine learning approaches. Appreciate the relationship between data quality and model performance. Identify key challenges in implementing machine learning systems. Machine learning sits at the heart of many modern AI systems, providing the ability to learn from data without explicit programming. Instead of relying on predefined rules, machine learning algorithms identify patterns, make predictions, and improve their performance over time through exposure to data. This adaptive learning capability is what sets machine learning apart and allows AI systems to tackle increasingly complex tasks. The process is akin to a child learning to ride a bicycle. They don't start with a perfect understanding of balance and coordination, but through trial and error, repeated practice, and feedback from their environment, falling, staying upright, they gradually refine their skills. Machine learning algorithms work in a similar way, iteratively refining their internal models based on the data they are exposed to. We can broadly categorize machine learning into three main types: supervised learning, unsupervised learning, and reinforcement learning. Each type uses a distinct approach to learning, and each is suited to different types of problems. Supervised learning. This is perhaps the most intuitive form of machine learning. Imagine you're training a dog new trick. You show the dog a desired behavior, e.g., sit, and reward it when it performs correctly. The dog learns to associate the command with the action, improving its performance over time. Supervised learning mirrors this process. The algorithm is provided with a labeled dataset, meaning the data includes both the input features and the corresponding correct output. For example, in image recognition, the dataset would consist of images labeled with the objects they depict, e.g., cat, dog, bird. The algorithm analyzes this data, identifying patterns that link the input features, pixel values in the image, to the correct output labels. Once trained, the algorithm can then predict the labels for new unseen images. Consider a spam filter. This is a prime example of supervised learning. We feed the algorithm a large dataset of emails, each labeled as either spam or not spam. The algorithm learns to identify patterns in the text and other features, sender, address, keywords, etc., that are characteristic of spam emails. Through this process, it learns to classify new emails as spam or not spam with increasing accuracy. The more data it's trained on, the better it gets at discerning the subtle differences between legitimate emails and spam. The labels spam or not spam are essential. They provide the feedback that guides the learning process. The accuracy of a supervised learning model is heavily reliant on the quality and quantity of the labeled data. A biased or incomplete dataset will lead to a biased or inaccurate model. For instance, if the spam filter is trained primarily on emails sent to one demographic, it might not perform as well when applied to emails sent to a different demographic, as the characteristics of spam could vary significantly between groups. Data cleaning, careful labeling, and a representative sample are therefore crucial steps in the development of effective supervised learning models. Unsupervised learning. Unlike supervised learning, unsupervised learning deals with unlabeled data. The algorithm is not given the correct answers. Instead, it's tasked with identifying patterns and structures within the data on its own. Think of it as giving a child a box of colorful blocks and asking them to sort them. The child might group blocks by color, shape, or size, discovering inherent patterns without any explicit instructions. Unsupervised learning algorithms operate similarly. They might cluster data points into groups based on similarity, reduce the dimensionality of the data to make it more manageable, or identify anomalous data points that deviate significantly from the norm. Customer segmentation in marketing is a good example of unsupervised learning. A company might use an unsupervised learning algorithm to group its customers based on their purchasing behavior, demographics, and other characteristics. This allows the company to tailor its marketing efforts to different customer segments, leading to increased effectiveness. The algorithm might discover segments like budget-conscious shoppers, high-value customers, or early adopters, all without being explicitly told what constitutes each segment. The algorithm learns these groupings from the inherent patterns and relationships within the data. Another application might involve anomaly detection, such as identifying fraudulent transactions based on deviations from typical spending patterns. Here, the algorithm learns what constitutes normal behavior and flags transactions that fall outside this established norm. Reinforcement learning. Reinforcement learning is a more complex type of machine learning. It involves an agent that interacts with an environment, taking actions and receiving rewards or penalties based on its actions. The agent learns to maximize its cumulative reward over time by selecting actions that lead to favorable outcomes. Think of a robot learning to navigate a maze. The robot receives a reward for reaching the goal and a penalty for hitting walls or taking too long. Through trial and error, the robot learns to optimize its path, maximizing its reward and minimizing its penalties. Games provide excellent examples of reinforcement learning. AI agents that have mastered games like chess, Go, and even complex video games have often been trained using reinforcement learning techniques. Ni et al. 2015. Silver et al. 2016. The agent learns through repeated play, receiving rewards for winning and penalties for losing. The more it plays, the more it refines its strategy, eventually achieving superhuman levels of performance. Self-driving cars are another promising application of reinforcement learning, where the agent learns to navigate traffic, obey traffic rules, and avoid accidents through interactions with the real-world environment. The reward function is designed to incentivize safe and efficient driving, while penalties are given for crashes or rule violations. The iterative process of trial, error, and reward guides the agent's learning. The key distinction between these types lies in the availability of labeled data and the nature of the feedback mechanism. Supervised learning utilizes labeled data, providing explicit feedback. Unsupervised learning explores unlabeled data, identifying inherent structures. Reinforcement learning learns through interaction and feedback, aiming for optimal actions in dynamic environments. The choice of which type of machine learning to use depends heavily on the specific problem, the nature of the available data, and the goals of the application. Each type offers powerful capabilities for extracting insights, making predictions, and driving automation in diverse fields. However, it's important to remember that machine learning is not a magic bullet. The effectiveness of these algorithms is highly dependent on the quality and relevance of the data used to train them. underscoring the importance of careful data preparation and pre-processing. Furthermore, the interpretation of the results requires understanding the limitations and potential biases of the models involved, ensuring responsible and ethical application of these powerful technologies. Amershi et al., 2019. Key takeaways. Machine learning enables systems to learn from data without explicit programming. Supervised learning uses labeled data to learn relationships between inputs and outputs. Unsupervised learning identifies inherent patterns in unlabeled data. Reinforcement learning trains through interaction with environments and feedback mechanisms. The effectiveness of all machine learning approaches depends heavily on data quality, deep learning, and neural networks. Learning objectives. Understand the architecture and functioning of artificial neural networks. Recognize how deep learning differs from traditional machine learning. Identify the key applications where deep learning excels. Appreciate the computational requirements of deep learning systems. Recognize both advantages and limitations of neural network approaches. Deep learning represents a significant advancement within machine learning. It leverages artificial neural networks, structures inspired by the biological neural networks of the human brain, but scaled up dramatically to handle vast amounts of data and complex tasks. Unlike simpler machine learning models that might struggle with intricate patterns, deep learning excels at uncovering hidden relationships within data, making it exceptionally powerful for a wide range of applications. The key to deep learning success lies in its architecture. Artificial neural networks with multiple layers. These layers, often described as hidden layers, allow the network to learn progressively more abstract representations of the input data. Think of it like a hierarchical processing system. The initial layers might detect simple features, such as edges and corners in an image. Subsequent layers combine these features to detect more complex patterns, such as shapes and objects. Finally, the output layer provides the final classification or prediction. This layered approach allows deep learning models to learn intricate and hierarchical representations of data, vastly increasing their capacity to solve complex problems that previously eluded simpler algorithms. To visualize this, imagine a neural network tasked with identifying a cat in an image. The first layer might detect basic features like edges and color gradients. The second layer might combine these features to recognize shapes like triangles and circles that comprise the cat's ears or eyes. Subsequent layers would combine these simpler shapes to detect more complex components, such as the cat's face, body, and tail. Finally, the output layer combines the information from all preceding layers to accurately classify the image as a cat. This multi-layered approach contrasts sharply with simpler machine learning models, which may struggle with the nuances and subtle complexities of visual data. A fundamental building block of deep learning is the artificial neuron, a computational unit inspired by the biological neuron. Each neuron receives input signals, processes them, and produces an output signal. These neurons are organized into layers, interconnected through weighted connections, and work in concert to process information. The weights of these connections represent the strength of the influence one neuron has on another, and they are adjusted during the learning process. The learning process itself is based on an iterative process of adjusting these weights to minimize the difference between the network's predictions and the actual values. This process, known as backpropagation, involves calculating the error in the network's output and then propagating this error back through the network to adjust the weights of the connections. The goal is to progressively refine the network's internal representation of the data until it consistently produces accurate predictions. This process requires massive datasets and significant computational power, often employing specialized hardware like GPUs, graphics processing units, to speed up training. Different types of neural networks exist, each designed to excel at specific tasks. Convolutional neural networks, CNNs, are particularly well suited for processing image data, leveraging their ability to detect spatial patterns and features. Recurrent neural networks, RNNs, on the other hand, are designed to process sequential data like text and speech, exploiting the temporal relationships within the data. Other specialized architectures, like generative adversarial networks, GNs, are used for generating new data, such as creating realistic images or composing music. Each of these architectures uses variations of the fundamental principles described above, adapting the layering and connectivity of neurons to optimize performance for specific applications. One of the most compelling aspects of deep learning is its ability to learn features automatically from raw data, eliminating the need for manual feature engineering, a laborious process often required in traditional machine learning. In image recognition, for example, a deep learning model can learn directly from the pixel values, automatically identifying relevant features like edges, textures, and shapes, without explicit programming. This automation reduces human effort and allows the model to adapt and improve with increasingly large datasets. The success of deep learning is not simply due to increased computational power. It also relies on the availability of large, labeled datasets. The more data a deep learning model is trained on, the better it becomes at identifying complex patterns and making accurate predictions. The sheer scale of data available today, coupled with advances in computing hardware, has fueled the remarkable progress we've witnessed in deep learning applications. Goodfellow et al. 2016. The practical applications of deep learning are vast and expanding rapidly. In image recognition, deep learning models have achieved superhuman performance in tasks such as object detection, facial recognition, and medical image analysis. LeCun et al. 2015. In natural language processing, NLP, deep learning powers advanced applications like machine translation, sentiment analysis, and chatbot development. In healthcare, deep learning assists in disease diagnosis, drug discovery, and personalized medicine. In finance, deep learning is used for fraud detection, algorithmic trading, and risk management. These are only a few examples demonstrating the broad impact of deep learning across multiple industries. However, deep learning is not without its challenges. The black box nature of these models, where the internal workings are often opaque, can make it difficult to understand why a particular prediction is made. This lack of transparency raises concerns in applications where explainability and trustworthiness are critical, such as medical diagnosis or judicial decisions. Weld and Bansal, 2019. Furthermore, deep learning models are often computationally expensive to train and deploy, requiring significant resources in terms of hardware and energy. Addressing these challenges, particularly the need for more transparent and explainable AI systems, is crucial for ensuring the responsible and ethical development and deployment of deep learning technologies. The field of deep learning is constantly evolving. with ongoing research focusing on developing more efficient architectures, improved training techniques, and addressing the challenges related to explainability and robustness. New deep learning models are continually emerging, demonstrating improved accuracy and efficiency across a variety of tasks. The ongoing development of more powerful hardware, algorithms, and theoretical understanding will undoubtedly continue to expand the capabilities and applications of deep learning in the years to come. The journey from simple machine learning to the sophisticated deep learning systems we have today highlights the rapid pace of innovation in artificial intelligence, opening up new frontiers of possibility across diverse domains. The ability of these systems to learn complex patterns from massive datasets marks a pivotal moment in technological advancement, transforming the way we interact with technology and approach complex challenges across multiple disciplines. As we progress, ethical considerations surrounding data privacy, algorithmic bias, and the societal impact of these powerful technologies remain paramount. The responsible development and deployment of deep learning should always be guided by principles of fairness, transparency, and accountability to ensure that these advances benefit all of humanity. Key takeaways. Deep learning uses neural networks with multiple layers to progressively learn more complex representations of data. The hierarchical structure of neural networks enables them to recognize patterns that evade simpler algorithms. Specialized neural network architectures like CNNs and RNNs are designed for specific types of data. Deep learning eliminates the need for manual feature engineering, but requires massive datasets and computational resources. While powerful, deep learning systems often lack transparency in their decision-making processes. AI in healthcare, diagnosis and treatment. Learning objectives. Identify key applications of AI in medical diagnosis and treatment. Understand how AI analyzes medical imaging and patient data. Recognize the potential of AI to improve healthcare outcomes. Appreciate the challenges in implementing AI healthcare solutions. Identify ethical considerations unique to AI in medical contexts. The integration of artificial intelligence, AI, into healthcare promises a revolution in how we diagnose, treat, and prevent diseases. AI's capacity to analyze vast datasets, identify complex patterns, and learn from experience offers unprecedented opportunities to improve patient outcomes and streamline healthcare processes. This transformative potential is most clearly seen in the areas of disease diagnosis and treatment. One of the most significant applications of AI in healthcare is in medical image analysis. Radiologists, pathologists, and other specialists often grapple with interpreting complex medical images like X-rays, CT scans, MRIs, and pathology slides. These images can be incredibly detailed, and subtle variations can hold the key to accurate diagnosis. AI algorithms, particularly those based on deep learning, are proving adept at identifying these subtle anomalies that might be missed by the human eye, even by experienced professionals. Topol, 2019. For instance, AI-powered systems can analyze mammograms to detect early signs of breast cancer with remarkable accuracy, potentially leading to earlier intervention and improved survival rates. Similarly, AI algorithms are being used to analyze retinal scans to detect diabetic retinopathy, a leading cause of blindness, and to identify signs of Alzheimer's disease through brain imaging. The impact extends beyond image analysis. AI is also transforming the process of disease diagnosis through the analysis of electronic health records, EHRs. EHRs contain a wealth of patient data, including medical history, lab results, and vital signs. AI algorithms can sift through this information to identify risk factors for specific diseases, predict the likelihood of future health problems, and even assist in formulating differential diagnoses, identifying multiple possible conditions based on a patient's symptoms. This capability can be particularly beneficial in diagnosing rare or complex conditions, where a definitive diagnosis might otherwise require extensive testing and consultation with multiple specialists. Furthermore, AI plays a crucial role in personalized medicine. One of the key aspects of personalized medicine is tailoring treatments to individual patients based on their unique genetic makeup, lifestyle, and medical history. AI algorithms can analyze this information to predict which treatments are most likely to be effective for a given patient, reducing the need for trial and error approaches and minimizing adverse effects. This is especially important in oncology, where cancer treatment can have significant side effects and require careful consideration of the patient's overall health. By leveraging AI, oncologists can make more informed treatment decisions, selecting the most appropriate therapies and minimizing the potential for harm. AI's contribution to drug discovery is equally transformative. The process of developing new drugs is notoriously long, expensive, and often unsuccessful. AI can significantly accelerate this process by analyzing vast databases of chemical compounds and biological information to identify potential drug candidates, predict their efficacy, and optimize their design. AI-powered systems can simulate the interaction of drug molecules with target proteins, allowing researchers to quickly screen millions of compounds and identify those most likely to be effective. This process accelerates the identification of promising lead compounds, ultimately reducing the time and cost required to bring new drugs to market. Beyond diagnosis and treatment, AI is also improving the efficiency and effectiveness of healthcare operations. AI-powered chatbots can answer patient queries, schedule appointments, and provide basic medical advice, freeing up healthcare professionals to focus on more complex tasks. AI can also optimize hospital bed allocation, predict patient flow, and improve resource management, leading to more efficient and cost-effective healthcare delivery. However, the integration of AI into healthcare is not without its challenges. One of the biggest concerns is the potential for algorithmic bias. AI algorithms are trained on data, and if that data reflects existing biases in healthcare, the algorithms may perpetuate and even amplify those biases. O'Neill, 2016. For example, if an algorithm is trained on data that predominantly reflects the experiences of one demographic group, it may not accurately predict the risk of disease or the effectiveness of treatment for other groups. This necessitates careful attention to data quality and algorithm design to ensure fairness and equity in the application of AI in healthcare. Another important consideration is data privacy and security. AI algorithms often require access to sensitive patient data, raising concerns about the potential for data breaches and misuse. Robust data security measures are essential to ensure that patient information remains confidential and protected. Furthermore, the black box nature of some AI algorithms can make it difficult to understand how they arrive at their conclusions, raising concerns about transparency and accountability. Explainable AI, XAI, is an emerging field focused on developing algorithms that are more transparent and easier to interpret, increasing trust and confidence in AI-driven healthcare solutions. The ethical implications of AI in healthcare are complex and multifaceted. The potential displacement of healthcare professionals, the need for ongoing monitoring and oversight of AI systems, and the potential for misuse are all important considerations. A careful and thoughtful approach is required to ensure that AI is used responsibly and ethically, ultimately benefiting both patients and healthcare providers. The future of AI in healthcare is bright, but realizing its full potential requires collaboration among researchers, clinicians, policymakers, and the public. By addressing the challenges and harnessing the opportunities presented by AI, we can transform healthcare into a more efficient, equitable, and effective system, improving the lives of millions around the world. Continued investment in research, development, and ethical considerations is critical to ensuring that the benefits of AI are widely accessible and that its potential risks are mitigated. The ongoing dialogue and collaborative effort required to navigate the ethical implications will be crucial in harnessing the true power of AI for the betterment of healthcare globally. The ultimate goal is not to replace human expertise, but to augment it, empowering healthcare professionals to make more informed decisions, deliver better care, and ultimately improve patient outcomes. This partnership between human intelligence and artificial intelligence represents a remarkable opportunity to reshape the future of healthcare for a healthier and more equitable world. Key takeaways. AI excels at analyzing complex medical images to detect subtle abnormalities. Electronic health record analysis enables AI to identify patterns and risk factors. Personalized medicine benefits from AI's ability to predict treatment efficacy for individual patients. AI accelerates drug discovery by screening millions of compounds efficiently. Ethical challenges include algorithmic bias, data privacy, and the need for transparency. AI in finance, fraud detection and risk management. Learning objectives. Identify key applications of AI in financial services. Understand how AI transforms fraud detection capabilities. Recognize AI's role in risk assessment and management. Evaluate the ethical implications of automated financial decisions. Assess the regulatory challenges presented by AI in finance. The financial sector, characterized by its high-stakes transactions and complex data streams, has embraced AI with remarkable enthusiasm. The ability of AI to process massive amounts of data at incredible speeds and identify subtle patterns invisible to the human eye has revolutionized how financial institutions manage risk, detect fraud, and make investment decisions. Let's delve into how AI is reshaping this critical industry. One of the most impactful applications of AI in finance is in fraud detection. Traditional fraud detection systems often rely on rule-based systems, which are inherently limited in their ability to adapt to evolving fraud techniques. These systems struggle to keep pace with the ever-increasing sophistication of fraudulent activities, often resulting in significant financial losses. AI, particularly machine learning algorithms, offers a more dynamic and adaptable approach. Machine learning algorithms, such as anomaly detection models, can analyze vast datasets of financial transactions, identifying patterns and anomalies that indicate fraudulent activity. These algorithms learn from past fraudulent transactions, constantly updating their models to identify new and emerging fraud patterns. Kaplan and Heinlein, 2019. This adaptive capability allows them to stay ahead of fraudsters, significantly improving the detection rate and reducing financial losses. For example, an algorithm might identify unusual spending patterns, such as a sudden surge in transactions from an unfamiliar location or an unusually large transaction for a particular account. These anomalies, which might be easily missed by human analysts, can trigger an alert, allowing financial institutions to investigate and prevent fraudulent activity. Furthermore, AI algorithms can be trained to identify more subtle forms of fraud that might be missed by traditional methods. For instance, AI can detect sophisticated schemes involving money laundering, where funds are moved through multiple accounts to obscure their origin. By analyzing intricate networks of transactions and identifying suspicious relationships between accounts, AI can uncover these complex schemes and prevent significant financial losses. The ability of AI to analyze unstructured data, such as emails and social media posts, further enhances its effectiveness in fraud detection. This capacity allows financial institutions to detect social engineering attacks, where fraudsters manipulate individuals into revealing sensitive information. The application of AI in algorithmic trading exemplifies AI's transformative power in finance. Algorithmic trading involves the use of computer programs to execute trades automatically based on predefined rules and algorithms. AI-powered algorithmic trading systems go beyond simple rule-based systems, employing machine learning algorithms to analyze market data, predict price movements, and execute trades with greater speed and accuracy. These systems can process enormous volumes of market data, including historical price data, news articles, social media sentiment, and economic indicators, to identify trading opportunities that might be missed by human traders. By combining quantitative analysis with predictive modeling, AI can generate more sophisticated trading strategies, leading to improved profitability and risk management. However, the use of AI in algorithmic trading also raises ethical concerns. The speed and automation of AI-driven trading can increase market volatility, as AI-powered systems react to market changes more rapidly than human traders. This raises concerns about market manipulation and the potential for systemic risk. The black box nature of some AI algorithms can also make it difficult to understand the rationale behind their trading decisions, raising concerns about transparency and accountability. To mitigate these risks, rigorous testing, transparent algorithm design, and strong regulatory oversight are crucial. AI plays a vital role in risk management, helping financial institutions assess and mitigate various types of risks. AI algorithms can analyze vast amounts of data, including credit scores, market trends, and macroeconomic indicators, to predict the likelihood of defaults, credit losses, and other financial risks. This predictive capability allows financial institutions to make more informed decisions about lending, investment, and risk mitigation strategies. For instance, AI can be used to assess the creditworthiness of borrowers, more accurately predicting the likelihood of loan defaults. This enables lenders to make more informed lending decisions, reducing the risk of loan losses. AI can also identify systemic risks in financial markets, providing early warnings of potential crises. By analyzing diverse data sources, AI can pinpoint vulnerabilities in the financial system, enabling timely intervention and mitigation efforts. AI algorithms can analyze large datasets of historical and real-time information to identify and manage operational risk. Operational risks include things like cyber attacks, system failures, and human errors. AI can assist in detecting anomalous behavior in systems, potentially signaling a cyber attack or a system malfunction. It can also be used to develop predictive models for various operational risks, allowing organizations to implement proactive measures to reduce their likelihood and impact. Furthermore, AI is transforming the field of regulatory compliance in the financial industry. Financial institutions are subject to numerous regulations designed to maintain the stability of the financial system and protect consumers. Compliance with these regulations requires processing huge amounts of data and identifying potential violations. AI can automate aspects of compliance monitoring, identifying patterns that might indicate regulatory breaches and flagging them for human review. This can greatly improve the efficiency of compliance procedures, reduce costs, and enhance the reliability of compliance reporting. However, the use of AI in risk management also faces certain challenges. One key challenge is ensuring the quality and reliability of the data used to train AI algorithms. If the data is biased or incomplete, the resulting AI models might produce inaccurate or misleading predictions. Another challenge is ensuring the explainability and transparency of AI models used in risk management. It's essential to understand how an AI model arrives at its conclusions, particularly in high-stakes financial decisions. The black box nature of some AI algorithms can make it difficult to interpret their predictions, potentially undermining trust and accountability. The need for explainable AI, XAI, is therefore paramount. The future of AI in finance is intertwined with the ongoing development of more sophisticated algorithms, better data handling techniques, and stronger regulatory frameworks. As AI algorithms become increasingly sophisticated, they will likely play an even more prominent role in fraud detection, algorithmic trading, and risk management. However, responsible development and deployment of AI are essential to mitigate potential risks. This includes addressing concerns about algorithmic bias, ensuring data privacy and security, and promoting transparency and accountability in AI-driven financial decisions. The ethical considerations surrounding the use of AI in finance will only become more complex, demanding a continual dialogue and collaboration among stakeholders, researchers, and policymakers to build a robust, secure, and equitable financial system. The ultimate goal is not simply to leverage AI for profit, but to create a financial system that is more transparent, secure, efficient, and beneficial for all. This requires a balanced approach, carefully weighing the transformative potential of AI against the risks it entails. Only through this thoughtful and collaborative approach can we ensure that AI serves as a force for good in the financial world. Zuboff, 2019. Key takeaways. AI significantly enhances fraud detection by identifying subtle patterns and anomalies in transaction data. Machine learning algorithms can adapt to evolving fraud techniques in ways traditional systems cannot. AI-powered algorithmic trading systems analyze market data to identify opportunities and execute trades. Risk management. Benefits from AI's ability to process diverse data and predict potential financial risks. Responsible AI deployment requires addressing bias, ensuring transparency, and establishing regulatory frameworks. AI in transportation, self-driving cars and logistics. Learning objectives. Understand the technology behind autonomous vehicles. Identify how AI optimizes transportation systems and logistics. recognize safety and regulatory challenges in transportation AI. Evaluate the potential economic impact of transportation automation. Consider ethical dilemmas specific to autonomous transportation systems. The transportation sector, a cornerstone of modern economies, is undergoing a dramatic transformation fueled by the rise of artificial intelligence. This revolution manifests most visibly in the development of self-driving cars. But its impact extends far beyond autonomous vehicles, significantly altering the landscape of logistics and supply chain management. Let's examine how AI is reshaping this vital industry. The dream of self-driving cars, once relegated to science fiction, is rapidly becoming a reality. These vehicles, also known as autonomous vehicles (AVs, rely on a sophisticated interplay of sensors, algorithms, and powerful computing capabilities to navigate roads and make driving decisions without human intervention. A multitude of sensors, including LiDAR, radar, and cameras, constantly monitor the vehicle's surroundings, collecting vast amounts of data on the environment, other vehicles, pedestrians, and road conditions. This raw data is then fed into complex algorithms, typically based on deep learning models, which interpret the information and make crucial decisions regarding steering, acceleration, braking, and lane changes. The algorithms used in self-driving cars are trained on massive datasets of driving scenarios, enabling them to learn from millions of miles of simulated and real-world driving data. This learning process allows the algorithms to recognize objects, anticipate the behavior of other road users, and make appropriate driving decisions. Deep learning, a subset of machine learning, is particularly well suited to this task, as its ability to extract complex patterns from large datasets allows the algorithms to adapt to a wide range of driving conditions and unforeseen situations. For example, the algorithms can learn to distinguish between a pedestrian crossing the street and a dog running across the road, and to adjust their driving behavior accordingly. They can also learn to recognize traffic signs, traffic lights, and road markings, and to adhere to traffic regulations. The decision-making process in self-driving cars is far more nuanced than simply following pre-programmed rules. The algorithms must constantly weigh competing objectives, such as maintaining a safe speed, staying within their lane, and avoiding collisions. They must also account for the unpredictable behavior of other road users, such as sudden lane changes or unexpected braking. To handle these complexities, self-driving car systems employ sophisticated decision-making algorithms, often incorporating elements of reinforcement learning, a type of machine learning where the algorithm learns by trial and error, receiving rewards for making correct decisions and penalties for making mistakes. This iterative learning process allows the algorithms to optimize their driving behavior over time. Beyond the individual vehicle, AI plays a crucial role in optimizing traffic flow and improving road safety. Intelligent transportation systems, ITS, leverage AI algorithms to analyze real-time traffic data, predicting congestion patterns, and suggesting optimal routes to drivers. This not only reduces travel times, but also contributes to a significant reduction in fuel consumption and greenhouse gas emissions. Furthermore, AI-powered traffic management systems can dynamically adjust traffic signals based on real-time traffic conditions, optimizing traffic flow and preventing congestion. By proactively identifying potential bottlenecks and adjusting traffic patterns accordingly, AI can help to prevent traffic jams and reduce the frustration associated with commuting. The potential for enhancing road safety is also immense. By constantly monitoring the driving environment, AI algorithms can detect potential hazards, such as pedestrians in blind spots or approaching vehicles, providing drivers with timely warnings and assistance, or even taking autonomous corrective action to prevent accidents. The integration of AI in logistics and supply chain management is revolutionizing how goods are moved around the globe. AI-powered systems optimize various aspects of the supply chain, from route planning and scheduling to inventory management and warehouse automation. Sophisticated route optimization algorithms, powered by machine learning, analyze vast amounts of data, including real-time traffic conditions, weather forecasts, and delivery deadlines, to determine the most efficient routes for transportation. This not only reduces delivery times, but also minimizes fuel consumption and transportation costs. AI also plays a significant role in optimizing warehouse operations. AI-powered robots are increasingly being deployed in warehouses to automate tasks such as picking, packing, and sorting, dramatically increasing efficiency and throughput. Predictive maintenance algorithms can forecast equipment failures, enabling proactive maintenance and minimizing downtime. Inventory management is another area significantly impacted by AI. AI-powered systems analyze historical sales data, current inventory levels, and future demand forecasts to optimize inventory levels, reducing storage costs while ensuring that goods are readily available to meet customer demand. Machine learning algorithms can identify patterns in sales data that might not be readily apparent to human analysts, enabling more accurate demand forecasting and reduced waste. The use of AI in logistics extends beyond individual companies and organizations. AI-powered platforms are emerging that connect various stakeholders in the supply chain, enabling better communication and collaboration. These platforms facilitate real-time information sharing, allowing for more efficient coordination of transportation, warehousing, and inventory management. However, the integration of AI in transportation also raises some challenges. The safety and reliability of self-driving cars are critical concerns. Ensuring that self-driving cars can handle unexpected situations and make safe driving decisions in complex environments requires robust algorithms and extensive testing. The ethical implications of AI-powered decision-making in self-driving cars are also a complex issue. In unavoidable accident scenarios, how should the algorithm prioritize the safety of passengers versus pedestrians or other road users? These are difficult questions that require careful consideration and ethical guidelines. Data privacy and security are also significant concerns. Self-driving cars collect vast amounts of data about their surroundings, raising concerns about the potential misuse of this data. Robust data security measures are essential to protect personal privacy. The future of AI in transportation holds immense promise, but realizing this potential requires a multifaceted approach involving technological advancements, robust regulatory frameworks, and public acceptance. The development of more sophisticated algorithms, enhanced sensor technologies, and reliable communication infrastructures are crucial for continued progress. Effective regulations are essential to address safety concerns, ensure ethical decision-making, and protect data privacy. Public trust and understanding of AI-powered transportation systems are also paramount to the widespread adoption of this transformative technology. As AI continues to evolve, we can expect further advancements in self-driving cars, optimized logistics, and intelligent transportation systems, shaping the future of transportation in profound ways. The efficient and safe movement of goods and people is fundamental to modern societies, and AI has the potential to make this transportation system more effective, sustainable, and safe for all. The journey towards fully realizing this potential requires ongoing research, development, and collaboration across various disciplines, ensuring that the benefits of AI are widely shared and its risks effectively managed. Chui et al., 2018. Key takeaways. Self-driving cars use a combination of sensors, deep learning algorithms, and computing power. AI optimizes traffic flow, routing, and transportation logistics in real time. Warehouse operations and inventory management benefit from AI-powered automation and prediction. Safety, ethics, and regulations present significant challenges for autonomous transportation. Public acceptance and trust are crucial for widespread adoption of AI transportation systems. AI in manufacturing, automation, and predictive maintenance. Learning objectives. Understand how AI enhances automation in manufacturing processes. Recognize the value of predictive maintenance in reducing downtime. Identify quality control applications of AI in production environments. Appreciate the economic impact of AI-enhanced manufacturing. Consider implementation challenges for manufacturing organizations. The transformative power of artificial intelligence, AI, extends far beyond the transportation sector, significantly impacting manufacturing processes and ushering in a new era of efficiency and productivity. AI's influence on manufacturing is multifaceted, encompassing automation of complex tasks, rigorous quality control, and the implementation of sophisticated predictive maintenance strategies. Let's delve into this dynamic interplay between AI and the manufacturing industry. One of the most visible applications of AI in manufacturing is the automation of tasks previously performed by humans. This automation doesn't simply involve replacing human workers with robots. Instead, it focuses on integrating intelligent systems that can perform complex, repetitive, or dangerous tasks with greater precision and efficiency than human counterparts. Consider the automotive industry, where robotic arms, powered by AI algorithms, perform intricate welding, painting, and assembly operations. These robots are not merely programmed to follow fixed sequences. They possess advanced sensor capabilities and AI-driven decision-making capabilities that allow them to adapt to variations in the production process. For example, an AI-powered robot welding two metal pieces might adjust its welding parameters in real time based on the detected temperature and consistency of the metal, ensuring a superior weld quality. This level of adaptive control is far beyond the capabilities of traditional robotic systems. Beyond the automotive sector, AI-powered robots are transforming manufacturing processes across various industries, including electronics, pharmaceuticals, and food processing. In electronics manufacturing, for example, AI-powered robots are used for the precise placement of tiny components onto circuit boards, a task requiring exceptional dexterity and accuracy. In pharmaceutical manufacturing, AI-powered robots can handle the delicate processes of drug formulation and packaging, ensuring sterility and precision. Even in food processing, AI-powered robots are used for tasks such as picking, sorting, and packaging, improving speed and reducing waste. Case study: semiconductor fabrication. A leading semiconductor manufacturer implemented an AI-driven automation system that reduced production errors by 38%, while increasing throughput by 25%. The system uses computer vision to inspect silicon wafers with nanometer precision, identifying defects invisible to the human eye. Machine learning algorithms continuously improve detection accuracy through feedback loops, adapting to new types of defects as they emerge. The economic impact has been substantial, an estimated $45 million in annual savings from reduced waste and improved yield based on industry reports. The integration of AI is not limited to robotic automation. It's equally impactful in refining quality control processes. Traditional quality control methods often rely on manual inspections, which are prone to human error and inefficiency. AI-powered vision systems, however, offer a far more precise and reliable approach to quality control. These systems employ advanced computer vision techniques to analyze images and videos of manufactured products, identifying defects that might be imperceptible to the human eye. For instance, in textile manufacturing, AI-powered vision systems can detect minute imperfections in fabric, ensuring consistent quality. Similarly, in the semiconductor industry, AI-powered vision systems can identify microscopic defects on silicon wafers, preventing faulty chips from reaching the market. These AI-driven quality control systems not only improve product quality, but also reduce waste by preventing the production of defective items. One of the most promising applications of AI in manufacturing is predictive maintenance. Predictive maintenance utilizes AI algorithms to analyze data from various sensors embedded in machinery to predict potential failures before they occur. This capability allows manufacturers to perform maintenance proactively, preventing costly downtime and maximizing equipment lifespan. Traditionally, maintenance has been largely reactive, meaning maintenance is performed only after equipment malfunctions. This reactive approach leads to unexpected downtime, significant repair costs, and potentially compromised product quality. Predictive maintenance, however, transforms this approach. Sensors within machinery continuously collect data on various parameters such as temperature, vibration, and pressure. This data is then fed into AI algorithms that learn to recognize patterns associated with impending failures. By analyzing historical data and real-time sensor readings, the AI algorithms can predict the likelihood of equipment failure with remarkable accuracy. This predictive capability enables manufacturers to schedule maintenance tasks proactively, minimizing downtime and maximizing equipment utilization. For example, an AI system monitoring a large industrial compressor might detect a slight increase in vibration, indicative of potential bearing wear. The system could then alert maintenance personnel, allowing for timely replacement of the bearing before it fails, thereby averting a costly and disruptive breakdown. This proactive approach to maintenance offers several significant advantages. Firstly, it reduces downtime by preventing unexpected equipment failures. Secondly, it optimizes maintenance schedules, ensuring that maintenance is performed only when necessary, minimizing the associated labor and material costs. Thirdly, it extends the lifespan of equipment by preventing catastrophic failures that could cause irreversible damage. Finally, it contributes to improved safety by identifying potential hazards before they can lead to accidents. The implementation of predictive maintenance systems can significantly reduce operational costs and improve overall production efficiency. Case study: automotive assembly line. An automotive manufacturer implemented an AI-based predictive maintenance system across 15 assembly plants worldwide. The system integrates data from over 50,000 sensors, analyzing patterns to predict equipment failures up to 3 weeks in advance. Since implementation, unplanned downtime has decreased by 47%, while maintenance costs have dropped by 28%. The predictive models continuously improve through machine learning, with each prevented failure providing new training data. The most significant benefit has been production reliability. Previously unpredictable line stoppages that disrupted complex supply chains have become rare, scheduled events. Company data validated by independent industry analysts. The integration of AI in manufacturing is not without its challenges. The initial investment in AI-powered systems can be substantial, requiring significant capital expenditures for hardware, software, and personnel training. Furthermore, the implementation of AI systems requires careful consideration of data security and privacy. The large volumes of data collected from machinery and sensors must be protected from unauthorized access and misuse. Ensuring data integrity and compliance with relevant regulations is critical. There is also a need for skilled personnel to develop, implement, and maintain AI-powered systems. Finding and training individuals with the necessary expertise is crucial for the successful integration of AI in manufacturing. However, the benefits of AI-driven automation, quality control, and predictive maintenance far outweigh the challenges. The potential for increased productivity, reduced costs, and improved product quality is significant. As AI technology continues to evolve and mature, its applications in manufacturing will become even more widespread and sophisticated. We can anticipate the development of AI systems capable of performing even more complex tasks, optimizing production processes to an unprecedented degree, and leading to the creation of highly efficient and adaptable manufacturing facilities. The integration of AI in manufacturing is not merely a technological advancement. It's a paradigm shift in how goods are manufactured, promising a future of greater efficiency, sustainability, and productivity. The future of manufacturing is undeniably intertwined with the continued development and adoption of AI technologies. The journey towards fully realizing this potential requires ongoing collaboration between researchers, manufacturers, and policymakers, ensuring that the benefits of AI are widely shared and its risks effectively mitigated. The result will be a more resilient, efficient, and technologically advanced manufacturing sector, poised to meet the demands of a rapidly changing global economy. Dung and Yu, 2014. Key takeaways. AI-powered automation in manufacturing goes beyond fixed programming to adaptive systems. Quality control benefits from computer vision systems that detect defects invisible to human inspectors. Predictive maintenance uses sensor data and machine learning to forecast equipment failures. The economic impact includes reduced downtime, improved quality, and extended equipment life. Implementation challenges include initial investment costs and the need for specialized expertise. AI in customer service, chatbots and personalization. Learning objectives. Understand how AI powers modern customer service chatbots. Recognize the technologies behind personalized customer experiences. Evaluate the business benefits of AI in customer interactions. Identify ethical considerations in automated customer service. Consider the balance between automation and human customer service. The revolution spurred by AI extends its reach into the realm of customer service, fundamentally altering how businesses interact with their clientele. This transformation is largely driven by the rise of chatbots and the sophisticated personalization of customer experiences. Chatbots, essentially AI-powered conversational interfaces, are rapidly becoming the first point of contact for many businesses, offering efficient and readily available support to customers around the clock. Their capacity to handle a large volume of queries simultaneously, coupled with their ability to learn and adapt over time, makes them a powerful tool for enhancing customer satisfaction and streamlining operational processes. The technology underlying chatbots is a fascinating blend of natural language processing, NLP, machine learning, ML, and deep learning, DL. NLP empowers chatbots to understand and interpret human language, allowing them to decipher the nuances of customer inquiries, even those containing colloquialisms, slang, or grammatical errors. Machine learning algorithms, constantly learning from interactions with customers, allow chatbots to improve their responses and resolve issues more accurately over time. This continuous learning process enhances the chatbot's efficiency and effectiveness in handling a wide spectrum of customer needs. DL, a subset of ML, plays a critical role in enabling chatbots to comprehend the context of conversations and provide more relevant and contextually appropriate responses. By analyzing vast amounts of data, DL algorithms help chatbots recognize patterns, anticipate customer needs, and ultimately provide a more human-like conversational experience. Different types of chatbots cater to various needs and levels of complexity. Rule-based chatbots operate on pre-programmed rules, responding to specific keywords or phrases. While simpler in design, they lack the adaptability of more advanced chatbots. Machine learning-based chatbots, on the other hand, utilize algorithms to learn from past interactions and adapt to new situations, offering more nuanced and context-aware responses. These chatbots are capable of handling a broader range of queries and can even engage in more open-ended conversations. The most sophisticated chatbots leverage deep learning techniques, enabling them to understand complex language structures, grasp the intent behind customer requests, and generate more human-like interactions. The choice of chatbot type depends heavily on the specific requirements of the business and the complexity of the customer interactions it needs to manage. The benefits of integrating chatbots into customer service are numerous and impactful. Firstly, chatbots offer 24/7 availability, providing instant support to customers regardless of time zone or business hours. This eliminates the frustration of waiting for responses during non-operating hours, significantly improving customer satisfaction. Secondly, chatbots can handle a high volume of queries concurrently, freeing up human agents to focus on more complex issues or interactions requiring a human touch. This efficiency boost reduces response times, increases customer satisfaction, and improves overall operational efficiency. Thirdly, chatbots can provide personalized experiences, tailoring their responses to the individual needs and preferences of each customer. This personalized approach fosters stronger customer relationships and enhances brand loyalty. However, the implementation of chatbots is not without its challenges. One major hurdle is ensuring that chatbots can accurately understand and respond to a wide range of customer queries. This requires extensive training data and meticulous testing to ensure the chatbot's ability to handle variations in language, slang, and colloquialisms. Furthermore, chatbots can struggle with complex or nuanced queries that require human empathy and understanding. In these situations, seamless handoff to a human agent is crucial to avoid frustrating customers. The ethical considerations of data privacy and the potential for biased responses also need careful consideration. Robust data security measures are essential to protect customer data, and ongoing monitoring and refinement are vital to prevent biases from creeping into the chatbot's responses. Beyond chatbots, AI is driving a new era of personalization in customer service. AI algorithms can analyze vast quantities of customer data, including purchasing history, browsing behavior, and interaction patterns, to create detailed customer profiles. This detailed understanding of customer preferences allows businesses to tailor their offerings and communications to individual needs, creating more relevant and engaging experiences. Personalized product recommendations, targeted marketing campaigns, and customized customer service interactions are just a few examples of how AI enhances the overall customer journey. Personalized recommendations, powered by AI algorithms, leverage data analysis to suggest products or services that are likely to interest each customer based on their individual preferences and past behavior. These recommendations can significantly increase sales and improve customer satisfaction by suggesting relevant items that align with individual tastes. Targeted marketing campaigns, tailored using AI-driven insights into customer demographics and behavior, improve the effectiveness of marketing efforts by ensuring that the right message reaches the right audience at the right time. This targeted approach maximizes the impact of marketing investments and minimizes wasted resources. Customize customer service interactions, informed by AI analysis of past interactions, enable customer service representatives to provide more relevant and efficient support. Having access to a customer's history enables faster troubleshooting and allows representatives to proactively address potential issues. Case study: e-commerce personalization. A major online retailer implemented an AI-driven personalization system that analyzes customer behavior across multiple channels. The system uses collaborative filtering algorithms to generate recommendations based not only on a customer's past purchases, but also their browsing patterns, time spent viewing items, seasonal trends, and even complementary product relationships. The results were impressive: a 31% increase in average order value and a 22% improvement in customer retention rates. The system continuously refines its understanding of each customer, creating increasingly accurate preference profiles that adapt to changing behaviors and preferences. This deep personalization has transformed the customer experience from generic to highly tailored, with 78% of customers reporting that recommendations feel surprisingly relevant to their specific needs, based on customer satisfaction surveys and transaction data. The ethical implications of utilizing AI for personalization are substantial and necessitate careful consideration. Data privacy is paramount. Customers must have control over their data and understand how it's being used. Transparency about data collection and usage practices is essential to build trust and maintain customer confidence. Furthermore, the potential for bias in AI algorithms needs careful scrutiny. If algorithms are trained on biased data, they may perpetuate and even amplify existing biases, leading to unfair or discriminatory outcomes. Continuous monitoring and auditing of AI algorithms are crucial to identify and mitigate such biases, ensuring fairness and equity in customer interactions. The responsible use of AI for personalization requires a commitment to ethical data practices, transparency and fairness, upholding customer rights, and protecting against potential harm. Arietta et al., 2020. The intersection of AI and customer service is constantly evolving. Future advancements in NLP, ML, and DL will likely lead to even more sophisticated and human-like chatbots. These chatbots will be capable of handling increasingly complex tasks, offering more seamless and intuitive interactions and providing a level of personalized support previously unimaginable. AI-powered tools will continue to enhance personalization efforts, allowing businesses to deliver ever more tailored experiences to their customers. However, navigating the ethical implications of AI-driven personalization remains a critical challenge. The ethical considerations of data privacy, algorithmic bias, and transparency will continue to shape the development and deployment of AI in customer service, emphasizing the need for responsible innovation and a commitment to ethical practices. The future of customer service is inextricably linked to the responsible and ethical development of AI technologies. Ensuring that these technologies serve to enhance the customer experience while upholding fundamental ethical principles. As AI continues to transform customer service, it will be crucial to strike a balance between technological advancement and ethical considerations, ensuring a future where AI empowers both businesses and customers. Key takeaways. AI-powered chatbots combine natural language processing, machine learning, and deep learning. 24/7 availability and high-volume query handling improve operational efficiency. AI enables sophisticated personalization through analysis of customer behavior and preferences. Ethical considerations include data privacy, transparency, and preventing algorithmic bias. Successful implementation requires balancing automation with human interaction for complex issues. Bias in AI systems, addressing fairness and equity. Learning objectives. Understand how bias enters AI systems through data and design. Recognize the social and ethical implications of biased AI. Identify methods for detecting bias in algorithms and datasets. Learn strategies for mitigating bias in AI development. Appreciate the importance of diverse teams in creating fair AI systems. The transformative power of AI, as we've seen, extends far beyond the realm of customer service. Its influence permeates nearly every facet of modern life, impacting everything from healthcare and finance to criminal justice and education. However, this very power brings with it a significant ethical burden: the potential for bias. AI systems, powerful as they are not inherently unbiased. They are trained on data. And if that data reflects existing societal biases, whether conscious or unconscious, the AI system will inevitably inherit and potentially amplify those biases. This subsection delves into the crucial issue of bias in AI systems, exploring its manifestations, consequences, and most importantly, the strategies for mitigating it. The genesis of bias in AI lies primarily in the training data. AI models, particularly those employing machine learning techniques, learn from the data they are fed. If this data contains skewed representations of certain demographic groups, the resulting AI system will likely reflect these imbalances in its decision-making. For instance, an AI system trained on facial recognition data, predominantly featuring individuals from a single ethnic background, might perform poorly and even inaccurately when identifying individuals from other backgrounds. This is not a case of the AI system being inherently racist, but rather a consequence of being trained on biased data that fails to capture the diversity of human features. Consider the implications for loan applications. If an AI system is trained on historical loan data, that shows a disproportionate number of loan defaults among a specific demographic group, the AI might unfairly deny loan applications from individuals belonging to that group, even if their financial circumstances warrant approval. This isn't just a theoretical concern. Such biases have been documented in real-world applications of AI in loan processing and other financial services. O'Neill, 2016. The system, trained on historical data reflecting existing inequalities, perpetuates and even exacerbates those inequalities. Similarly, bias in AI can have devastating consequences in the criminal justice system. An AI system used to predict recidivism, the likelihood of re-offending, might be trained on data that overrepresents certain racial or socioeconomic groups, leading to biased predictions that disproportionately flag individuals from those groups as high risk. This could result in unfairly harsher sentences or parole denials, further entrenching existing inequalities. Such instances highlight the profound societal impact of biased AI, showcasing its capacity to perpetuate and amplify existing injustices. The problem extends beyond readily identifiable biases like race and gender. Other forms of bias, such as those based on socioeconomic status, geographic location, or even age, can equally affect the fairness and equity of AI systems. For example, an AI system designed to assess the creditworthiness of individuals might inadvertently discriminate against individuals from rural areas if the training data predominantly reflects urban populations and their spending habits. The seemingly neutral parameters of the AI could mask a deep-seated bias stemming from an incomplete or skewed dataset. The implications of biased AI are not merely theoretical. They have real-world consequences, impacting individuals and communities. In healthcare, a biased AI system used for diagnosis or treatment recommendations could lead to misdiagnosis or inadequate treatment for certain demographic groups. In education, biased AI systems used for student assessment could lead to unfair evaluations and potentially limit opportunities for certain students. The pervasiveness of AI across different sectors necessitates a critical examination of its potential for bias and the development of robust strategies to mitigate it. Case study: Healthcare diagnostic bias. A research team discovered significant disparities in a widely used AI diagnostic system for detecting skin cancer. The system demonstrated 99% accuracy for light-skinned patients, but only 67% accuracy for those with darker skin tones. Investigation revealed the training dataset contained over 80% images from light-skinned patients. The team implemented a comprehensive bias mitigation strategy. 1. They created a balanced training dataset with equal representation across skin types. 2. They developed specialized image processing techniques to better identify cancer indicators in darker skin. 3. They implemented a fairness constraint algorithm that balanced false positive or negative rates across demographic groups. And 4. They established an ongoing monitoring protocol with regular equity audits. After these interventions, the diagnostic accuracy gap narrowed to less than 3% between demographic groups. This case demonstrates how bias can be systematically addressed through a combination of data interventions, algorithmic adjustments, and continuous monitoring, data from published clinical studies. Addressing bias in AI requires a multi-pronged approach. First and foremost, it necessitates a careful examination and curation of the training data. This involves actively seeking out and incorporating data that accurately represents the diversity of the population for which the AI is intended. This process often requires significant effort to identify and correct imbalances in existing datasets. Data augmentation techniques, which involve generating synthetic data to supplement existing datasets, can help address imbalances. But careful consideration is crucial to prevent the introduction of new biases. Beyond data curation, the algorithms themselves need to be carefully designed and tested for bias. This involves employing techniques such as fairness-aware algorithms that explicitly incorporate fairness constraints into the model training process. These algorithms are designed to minimize disparities in outcomes across different demographic groups. Furthermore, rigorous testing and evaluation of the AI system are crucial. This involves assessing the system's performance across various demographic groups to identify any disparities in accuracy or fairness. Transparency is another critical aspect of mitigating bias. The development and deployment of AI systems should be accompanied by clear documentation of the data sources, the algorithms used, and the testing procedures employed. This allows for external scrutiny and facilitates the identification of potential biases. Furthermore, making the underlying data and algorithms accessible to researchers and policymakers can foster greater transparency and accountability. Collaboration and interdisciplinary approaches are also critical. The development of fair and equitable AI systems requires collaboration between AI researchers, ethicists, social scientists, and policymakers. This collaborative approach brings together diverse perspectives and expertise to ensure that ethical considerations are integrated throughout the AI lifecycle. Regular audits and ongoing monitoring of AI systems in deployment are essential to identify and correct biases that may emerge over time. The ethical responsibility for mitigating bias in AI rests primarily with the developers and deployers of these systems. They have a moral and societal obligation to ensure that the AI systems they create are fair, equitable, and do not perpetuate or amplify existing societal biases. This responsibility extends beyond technical expertise, requiring a deep understanding of the social and ethical implications of their work. It necessitates a commitment to transparency, accountability, and a willingness to continuously learn and adapt as new challenges emerge. Ultimately, the pursuit of fair and equitable AI is not merely a technical challenge, but a societal imperative. The potential for AI to exacerbate existing inequalities is a serious concern that demands proactive and comprehensive solutions. By embracing a multifaceted approach that includes careful data curation, bias-aware algorithms, rigorous testing, transparency, collaboration, and a deep commitment to ethical principles, we can strive towards the development of AI systems that serve all members of society justly and fairly. This requires ongoing vigilance, a commitment to continuous improvement, and a recognition that the quest for fairness in AI is an ongoing process, requiring constant adaptation and refinement. Only through collective action and a shared responsibility can we harness the power of AI while mitigating its potential for harm. Key takeaways. AI systems inherit biases present in their training data, potentially amplifying societal inequalities. Biased AI can have severe consequences across healthcare, finance, criminal justice, and education. Addressing bias requires comprehensive strategies, including diverse data collection and algorithm design. Transparency, collaboration, and interdisciplinary approaches are essential for creating fair AI. Ongoing monitoring and auditing are necessary, as bias can emerge or evolve over time. Job displacement and the future of work. Learning objectives. Understand how AI automation affects different employment sectors. Identify jobs most vulnerable to automation and those likely to remain stable. Recognize strategies for workforce transitions in an AI-driven economy. Evaluate policy approaches to address AI-related job displacement. Consider how human-AI collaboration might reshape work environments. The transformative power of AI, as discussed earlier, extends to the very fabric of our economic systems, raising profound questions about the future of work. While AI offers unprecedented opportunities for productivity and innovation, it also casts a shadow of uncertainty over the employment landscape, prompting anxieties about widespread job displacement. This shift, however, is not simply a matter of machines replacing humans. It's a complex interplay of technological advancement, economic restructuring, and societal adaptation. Understanding the challenge, scope, and scale. One of the most pressing concerns is the potential for automation to render certain jobs obsolete. Repetitive manual tasks, along the backbone of many industries, are particularly vulnerable. Manufacturing, transportation, and logistics, for example, have already seen significant automation, with robots and automated systems taking over roles previously performed by human workers. This trend is expected to accelerate, potentially leading to significant job losses in these sectors. However, the narrative is not purely one of loss. While some jobs will be eliminated, others will be transformed, requiring new skills and expertise. The impact of AI on the job market is not uniform. Certain professions are more susceptible to automation than others. Jobs requiring highly repetitive, rule-based tasks are most at risk. This includes data entry clerks, factory workers performing assembly line tasks, and truck drivers on predictable routes. These jobs are largely characterized by predictable, repetitive actions that can be easily programmed into automated systems. Conversely, jobs requiring creativity, critical thinking, complex problem-solving, emotional intelligence, and interpersonal skills are less likely to be fully automated in the foreseeable future. Occupations in fields like healthcare, education, and social work, which necessitate human interaction and nuanced judgment, are anticipated to remain relatively resilient to the immediate effects of automation. However, even within professions considered resistant to complete automation, AI is likely to transform the nature of work. Consider the field of law. AI-powered tools can now assist with legal research, contract review, and even the prediction of court outcomes. While this does not eliminate the need for human lawyers, it alters their roles, demanding increased proficiency in working alongside AI tools and interpreting their outputs. This highlights a crucial aspect of the AI-driven workforce shift: the need for upskilling and reskilling. A framework for addressing AI-driven job displacement. The tension between job displacement fears and productivity opportunities requires a structured approach. 1. Short-term mitigation strategies, targeted retraining programs for vulnerable workers, transitional income support during career shifts, investment in education systems that develop AI complementary skills. Second, medium-term, adaptation mechanisms, industry education partnerships to anticipate skill demands, development of new job categories that leverage AI capabilities, redesign of existing roles to incorporate human-AI collaboration. 3. long-term structural solutions, economic policy innovation, e.g., universal basic income trials, redefinition of work and value creation in an automated economy, distributed ownership models for AI-driven productivity gains, the historical precedent of technological transitions, from agricultural to industrial to information economies, suggests that while disruption is inevitable, net employment can grow through proactive policy, education reform, and responsible innovation practices. The key distinction of the AI transition is its pace and breadth, requiring more deliberate management than previous technological shifts. Brynjolfsson and McAfee, 2014. Educational transformation and workforce development. The challenge before us is not merely to mitigate job losses, but to proactively prepare the workforce for a future defined by collaboration between humans and AI. This requires a fundamental shift in education and training, focusing on the development of skills complementary to AI capabilities. Emphasis should be placed on critical thinking, problem-solving, creativity, and adaptability skills that are less susceptible to automation. Furthermore, fostering digital literacy and proficiency in data analysis are crucial, as these skills are increasingly essential across various industries. Retraining initiatives will be essential in helping displaced workers transition to new roles. Government policies and private sector investments should support the development of effective retraining programs that provide workers with the skills necessary to navigate the changing job market. These programs should not just be focused on technical skills, but also on broader skills like communication, teamwork, and adaptability, qualities that are highly valued in collaborative work environments. Furthermore, lifelong learning should be encouraged, with programs offering continuous upskilling opportunities throughout a worker's career to keep pace with the rapid evolution of technology. Case study: manufacturing workforce transition. A manufacturing company facing automation of 40% of its production jobs implemented a comprehensive workforce transition program. Instead of mass layoffs, they created a 3-track approach. 1. Technical upskilling for employees who could transition to maintaining and programming the new automated systems. 2. Cross-training for service-oriented roles within the company, leveraging workers' institutional knowledge. And 3. Partnerships with local community colleges to provide broader career retraining with full tuition support. The company invested $8.2 million in the program, equivalent to about 60% of the projected first-year savings from automation. Within 18 months, 78% of affected employees had successfully transitioned to new roles, either within the company or with partner organizations. The company reported increased employee loyalty, knowledge retention, and a smoother implementation of automated systems compared to industry peers who took a layoff-based approach. The program has since become a model for ethical automation in the manufacturing sector. The transition will not be without its challenges. The speed at which AI-driven automation is progressing necessitates rapid and comprehensive responses. Addressing potential job displacement requires proactive measures to anticipate shifts in the job market and to provide support for workers affected by automation. This involves not only retraining programs, but also the development of social safety nets, such as unemployment benefits and income support programs, to help workers navigate periods of transition. The opportunities presented by AI, however, must not be overlooked. The increased productivity and efficiency offered by AI can lead to economic growth and the creation of new jobs in fields that support and develop AI technologies. The demand for AI specialists, data scientists, and AI ethicists is already increasing rapidly. Moreover, AI can free up human workers from mundane tasks, allowing them to focus on more complex, creative, and fulfilling aspects of their work. A balanced perspective is crucial. While acknowledging the potential for job displacement, we must simultaneously recognize the opportunities for economic growth, improved productivity, and the creation of new, higher-skilled jobs. The key lies in proactively preparing the workforce for this transition through targeted retraining and upskilling programs, investment in education and research, and the development of social safety nets to support those affected by automation. The societal impact extends beyond individual job security. The integration of AI into the workforce has broader economic and social consequences. The distribution of wealth may become increasingly unequal if the benefits of AI-driven productivity gains are not widely shared. Policies promoting equitable access to education, training, and economic opportunities are essential to ensure that the benefits of AI are not concentrated in the hands of a few. Furthermore, the potential for AI bias to exacerbate existing inequalities in the labor market requires vigilant monitoring and mitigation strategies. The ethical considerations are paramount. The use of AI in the workplace must be governed by ethical guidelines that prioritize human well-being and dignity. Concerns about data privacy, algorithmic transparency, and the potential for AI to reinforce existing biases need to be addressed proactively. Legislation and regulation play a crucial role in establishing frameworks for the responsible development and deployment of AI technologies in the workplace. The transition to an AI-driven workforce demands a concerted effort from governments, businesses, and educational institutions. Governments must invest in retraining programs, support social safety nets, and develop regulatory frameworks that promote ethical and responsible AI development. Businesses need to invest in the reskilling of their workforce and adopt responsible AI practices. Educational institutions have a crucial role to play in preparing students for the future of work by equipping them with the skills and knowledge necessary to thrive in an AI-driven economy. In conclusion, the impact of AI on employment is a multifaceted issue demanding a comprehensive and proactive response. While the potential for job displacement is real, the opportunities for economic growth, improved productivity, and the creation of new jobs are equally significant. By addressing the challenges head-on through retraining initiatives, investment in education, responsible AI development, and robust social safety nets, we can navigate this transition successfully and harness the transformative power of AI for the benefit of all. This requires a continuous process of adaptation, collaboration, and a deep commitment to ensuring that the benefits of AI are broadly shared and its potential harms are effectively mitigated. The future of work is not merely about surviving the technological shift. It's about shaping it to build a more just and equitable society. Harari, 2018. Key takeaways. Jobs involving routine, predictable tasks face the highest risk of automation. AI will transform most professions, requiring new skills and human-AI collaboration. Educational systems must evolve to emphasize uniquely human capabilities and technical literacy. A comprehensive approach includes short-term mitigation, medium-term adaptation, and long-term structural solutions. The transition requires coordination between government policy, business practices, and educational initiatives. Privacy concerns and data security. Learning objectives. Understand the privacy implications of AI systems that collect and analyze personal data. Identify key vulnerabilities in AI data processing pipelines. Recognize regulatory frameworks addressing AI privacy and security. Learn technical approaches for privacy-preserving AI. Evaluate the balance between data utilization and privacy protection. The previous section explored the profound impact of AI on the workforce, highlighting the need for adaptation and proactive measures to mitigate potential job displacement. However, the societal implications of AI extend far beyond the realm of employment. A crucial aspect of the ethical landscape surrounding AI is the complex interplay between privacy concerns and data security. The very power of AI, its ability to learn and adapt from vast datasets, is intrinsically linked to the collection and analysis of personal data. This presents a critical challenge. How can we harness the transformative potential of AI while simultaneously safeguarding the privacy and security of individuals? The exponential growth of data collection in the age of AI is unprecedented. From social media interactions and online shopping to healthcare records and financial transactions, our digital footprints are constantly expanding. AI systems, fueled by machine learning algorithms, rely on these vast troves of data to function effectively. This dependence, however, creates inherent vulnerabilities. The more data an AI system has access to, the greater the potential for misuse or unauthorized access. The sheer volume of data also makes it challenging to implement comprehensive security measures, increasing the risk of data breaches and privacy violations. One of the most significant concerns is the lack of transparency in how AI systems utilize personal data. Many AI algorithms are complex black boxes, making it difficult to understand how decisions are made or what factors contribute to a particular outcome. This opacity can lead to biases and discriminatory outcomes, particularly when applied to sensitive areas like loan applications, hiring processes, or even criminal justice. If an AI system decides that negatively impacts an individual, the lack of transparency can make it challenging to understand the reasoning behind that decision and seek redress. Furthermore, the potential for data breaches and unauthorized access is a constant threat. AI systems often process sensitive personal information, including financial details, health records, and biometric data. A successful data breach could expose this information to malicious actors, leading to identity theft, financial fraud, or even physical harm. The sophisticated nature of modern AI systems, however, also presents challenges for traditional cybersecurity measures. AI-powered attacks are becoming increasingly common, employing advanced techniques to bypass conventional security protocols. Therefore, maintaining data security in the face of evolving cyber threats requires continuous innovation and adaptation. Key privacy-preserving technologies. To address these challenges, researchers have developed specialized techniques that allow AI systems to learn from data while protecting individual privacy. Differential privacy. A mathematical framework that adds carefully calibrated noise to data or analysis results. It guarantees that the presence or absence of any individual's data has a negligible impact on the output, protecting individual privacy while maintaining statistical validity. For example, when analyzing hospital records, differential privacy might slightly alter aggregate statistics while making it mathematically impossible to determine if a specific person's record was included. Federated learning, a machine learning approach where the model is trained across multiple devices or servers without exchanging the actual data. Instead of sending private data to a central server, the model travels to the data, trains locally, and only model updates, not the raw data, are shared and aggregated. This enables collaborative learning while keeping sensitive data on original devices. For instance, smartphone keyboards can improve text prediction by learning from users' typing patterns without ever sending the actual text to central servers. Weld and Bansal, 2019. Homomorphic encryption. This technique allows computations to be performed on encrypted data without decrypting it first. The results, when decrypted, are identical to those that would have been obtained from operations on the unencrypted data. This allows AI systems to analyze sensitive information without actually seeing the raw data, significantly reducing privacy risks. Figure 13. Privacy-preserving AI technologies and their applications. Regulations such as the General Data Protection Regulation, GDPR in Europe, and the California Consumer Privacy Act, CCPA, in the United States represent significant steps towards addressing these concerns. These regulations aim to give individuals more control over their personal data, including the right to access, correct, and delete their data. They also impose obligations on organizations to implement robust data security measures and to obtain informed consent for the collection and processing of personal data. While these regulations are crucial, their enforcement and effectiveness vary across jurisdictions, and the rapid pace of technological development often outstrips the capacity of regulatory bodies to keep up. The ethical implications of data collection and usage extend beyond compliance with specific regulations. Responsible data handling involves a commitment to transparency, accountability, and fairness. Organizations should be transparent about how they collect, use, and protect personal data, providing clear and concise explanations to individuals. Accountability mechanisms are essential to address any instances of data misuse or breaches. Individuals should have avenues to report concerns and seek redress for any harm caused by the misuse of their data. Furthermore, AI systems should be designed and deployed in a fair and unbiased manner, minimizing the risk of discriminatory outcomes. Beyond legislative frameworks and regulatory bodies, a strong ethical compass within the AI development community is paramount. This involves a proactive approach to mitigating risks associated with AI systems, including the implementation of privacy-preserving technologies, such as differential privacy and federated learning. These techniques allow for the analysis of data without compromising individual privacy by adding noise to the data or keeping the data decentralized, reducing the risk of breaches. Case study: healthcare. Data protection. A healthcare AI startup developing diagnostic algorithms faced a critical challenge: how to train their models on sensitive patient data while maintaining privacy and regulatory compliance. They implemented a multi-layered privacy protection system. 1. All patient data was de-identified according to hyper-standards before processing. 2. They employed federated learning, allowing their models to train across multiple hospitals without the data ever leaving each institution's secure servers. 3. They added differential privacy guarantees, ensuring individual patients couldn't be re-identified from the model outputs. And 4, they implemented homomorphic encryption for certain highly sensitive analyses. The system underwent independent security audits and received certification from privacy advocacy organizations. This comprehensive approach not only protected patient privacy, but also facilitated partnerships with healthcare institutions that had previously been hesitant to share data. The resulting diagnostic system achieved high accuracy while maintaining patient trust and regulatory compliance. This case demonstrates how multiple privacy-preserving technologies can be combined to enable AI advancement while protecting sensitive personal information. Educating the public about the risks and benefits of AI is another vital step towards fostering a responsible AI ecosystem. Individuals need to be informed about how their data is being collected and used, and they need to be empowered to make informed decisions about their privacy. Promoting digital literacy and critical thinking skills can help individuals navigate the complex landscape of data collection and AI-driven systems, empowering them to understand and protect their rights. The future of AI is inextricably linked to our ability to address these privacy concerns and ensure data security. This requires a multifaceted approach involving collaboration between governments, industry, and academia. Governments need to develop and enforce robust data protection regulations, keeping pace with the rapid evolution of technology. Industries must invest in data security measures and adopt responsible data handling practices, prioritizing transparency and accountability. Academia plays a critical role in developing privacy, preserving technologies, and educating the next generation of AI professionals on the ethical implications of their work. The ethical considerations surrounding AI are not merely abstract philosophical discussions. They have tangible and immediate consequences for individuals and society. The protection of privacy and the safeguarding of data security are not optional add-ons, but fundamental prerequisites for the responsible development and deployment of AI. Only through a concerted effort to address these crucial issues can we harness the transformative potential of AI while upholding the values of fairness, transparency, and individual autonomy. The development of AI must be guided by a commitment to protecting fundamental rights, ensuring that this powerful technology serves humanity, not the other way around. Ignoring these ethical considerations risks creating a world where technological progress comes at the unacceptable cost of individual liberty and societal well-being. The path forward requires a delicate balance, fostering innovation while simultaneously prioritizing the rights and security of every individual. Zuboff, 2019. Key takeaways. AI systems require massive datasets, creating inherent privacy and security vulnerabilities. The opacity of AI decision-making processes compounds privacy concerns and accountability issues. Privacy-preserving technologies, like differential privacy and federated learning, offer technical solutions. Regulatory frameworks provide important protections, but struggle to keep pace with technological advancement. Responsible AI development requires balancing innovation with robust privacy protections. AI and autonomous weapons systems. Ethical dilemmas. Learning objectives. Understand what constitutes autonomous weapons systems, AWS. Recognize the technical capabilities and limitations of AWS. Identify key ethical concerns raised by military AI applications. Evaluate international governance approaches to AWS. Consider the role of human oversight in weapons systems. The ethical minefield surrounding artificial intelligence extends far beyond data privacy and security. It delves into the realm of autonomous systems, particularly those capable of lethal action autonomous weapons systems, AWS. The prospect of machines making life-or-death decisions without direct human intervention presents profound ethical challenges that demand careful consideration. The core of the dilemma lies in the potential erosion of human control over the use of force, a fundamental principle underpinning international humanitarian law and just war theory. Historically, the decision to deploy lethal force has rested with humans, subject to various legal, moral, and political constraints. This human element, however flawed it may be, provides a degree of accountability and a capacity for judgment that sophisticated algorithms, even the most advanced, may lack. The delegation of this critical decision to an autonomous system raises concerns about the potential for unintended consequences, errors in judgment, and the erosion of human responsibility. Consider the potential for algorithmic bias to manifest in AWS. If an AWS is trained on data reflecting existing societal biases, it could perpetuate and even amplify those biases in its lethal decision-making. For example, if the training data overrepresents certain ethnic or racial groups as threats, the AWS might exhibit discriminatory targeting patterns. The opacity of many AI algorithms further complicates this issue. Understanding how an AWS arrives at a decision to engage a target can be exceedingly difficult, making it challenging to identify and correct biases or errors. This lack of transparency not only undermines accountability, but also inhibits effective oversight and regulation. The potential for malfunction or hacking is another significant concern. Even the most robustly engineered AWS is susceptible to errors or malfunctions, potentially leading to unintended harm. The possibility of malicious actors gaining control of an AWS and using it for nefarious purposes is equally alarming. The potential for escalation of conflicts through autonomous systems is also a major worry. The rapid pace of decision-making inherent in AWS could accelerate conflict dynamics, potentially triggering unintended and devastating consequences. The argument for AWS often centers on the potential benefits in terms of reduced casualties and improved battlefield effectiveness. Proponents suggest that AWS can make more accurate and efficient targeting decisions than humans, minimizing civilian casualties and collateral damage. They argue that AWS can operate in dangerous environments and carry out tasks too hazardous for human soldiers. Furthermore, some proponents point to the potential for AWS to deter aggression through their ability to respond swiftly and decisively. However, these purported benefits are often countered by strong arguments, highlighting the inherent risks and ethical challenges. The lack of human judgment and emotional intelligence in AWS is a critical concern. Human soldiers can consider the broader context of a situation, taking into account factors such as the potential for unintended harm, the overall strategic objectives, and the ethical implications of their actions. An AWS, operating purely on algorithms and pre-programmed parameters, may not possess this nuanced understanding of the battlefield and its ramifications. The question of accountability also lies at the heart of the debate. When an AWS causes harm, who is responsible? Is it the developers, the manufacturers, the operators, or the state deploying the system? The complexities of establishing clear lines of accountability in the case of AWS accidents or intentional misuse raise significant legal and ethical hurdles. International humanitarian law, and indeed common sense, demands that lethal force be used only as a last resort, and with strict adherence to principles of proportionality and distinction. Can an AWS reliably uphold these principles in the unpredictable and often chaotic circumstances of warfare? The potential for unintended escalation and the erosion of human control over life or death decisions pose serious risks to global security and stability. The potential for an arms race fueled by AWS is equally alarming, with the prospect of autonomous weapons proliferating in the hands of both state and non-state actors. Case study: International Dialogue on AWS Governance. A multinational initiative brought together military experts, AI researchers, ethicists, and diplomats from 42 countries to develop governance principles for autonomous weapons systems. The dialogue acknowledged both security concerns and ethical imperatives, resulting in a framework that balanced technological innovation with humanitarian protections. Key outcomes included: 1. A tiered classification system for autonomy in weapons, with corresponding oversight requirements. 2. Mandatory, meaningful human control standards, requiring human approval for lethal force against human targets. 3. Verification protocols for AWS compliance with international humanitarian law. 4. Technical standards for fail-safe mechanisms and cyber protection. Case study: International Dialogue on AWS Governance. A multinational initiative brought together military experts, AI researchers, ethicists, and diplomats from 42 countries to develop governance principles for autonomous weapons systems. The dialogue acknowledged both security concerns and ethical imperatives, resulting in a framework that balanced technological innovation with humanitarian protections. Key outcomes included: 1. A tiered classification system for autonomy in weapons, with corresponding oversight requirements. 2. Mandatory, meaningful human control standards, requiring human approval for lethal force against human targets. 3. Verification protocols for AWS compliance with international humanitarian law. 4. Technical standards for fail-safe mechanisms and cyber protection. And 5. A joint monitoring body with representatives from diverse stakeholder groups. While not legally binding, these principles have been voluntarily adopted by major military powers and influence national policy development. This case demonstrates how multidisciplinary collaboration can produce practical governance frameworks that address both the technical and ethical dimensions of emerging AI weapon technologies. The absence of an international legal framework, specifically governing the development and use of AWS, underscores the urgency of addressing these ethical challenges. While existing international humanitarian law provides a framework for the conduct of warfare, it does not fully address the unique challenges presented by autonomous systems. International cooperation and consensus building are crucial to establishing clear norms, rules, and regulations for the development, deployment, and oversight of AWS. The ethical debate surrounding AWS necessitates a careful balancing act. The potential benefits of improved precision and reduced risk to human soldiers must be weighed against the potential for unintended harm, loss of human control, and the erosion of accountability. Technological advancement should not come at the cost of human dignity, ethical principles, and international security. The development and deployment of AWS necessitate careful consideration of international law, ethical guidelines, and responsible technological governance. Global cooperation and informed public discourse are crucial in navigating this complex ethical landscape. The future of warfare depends on it. Avoiding a future dominated by autonomous killing machines requires proactive and decisive action at both the national and international levels. Ignoring this challenge will not make it disappear. It will only increase the risks. The path forward necessitates global collaboration, rigorous ethical debate, and an unwavering commitment to the humanitarian principles that underpin the very fabric of international law. The ultimate goal should not be the development of increasingly sophisticated weapons, but the creation of a more peaceful and secure world for all. Bostrom, 2014. Key takeaways. Autonomous weapon systems raise profound questions about human control over lethal force. AI bias and opacity create particular concerns in systems with life or death decision capabilities. Accountability challenges emerge when determining responsibility for AWS actions. International humanitarian law principles like proportionality may be difficult to encode algorithmically. Effective governance requires international cooperation and multidisciplinary approaches. The future of AI governance and regulation. Learning objectives. Understand current approaches to AI regulation across jurisdictions. Identify key principles for effective AI governance frameworks. Recognize the balance between innovation and protection in regulation. Evaluate the role of industry self-regulation versus government oversight. Consider international cooperation challenges in global AI governance. The preceding discussion highlighted the profound ethical dilemmas posed by autonomous weapon systems. A particularly stark example of the broader challenges inherent in the unchecked advancement of artificial intelligence. However, the ethical considerations extend far beyond the battlefield, permeating every aspect of AI's integration into society. This necessitates a comprehensive framework for AI governance and regulation. A task fraught with complexities, but undeniably crucial for a future where AI's influence continues to grow. The development of robust AI governance frameworks presents a significant challenge, demanding a delicate balance between fostering innovation and mitigating potential harms. An overly restrictive regulatory environment could stifle the progress that AI promises across various sectors, hindering advancements in healthcare, environmental sustainability, and economic productivity. Conversely, an absence of regulation could unleash AI's potential for harm, exacerbating existing inequalities, eroding privacy, and even posing existential risks. One approach to AI regulation focuses on establishing specific guidelines and standards for the development and deployment of AI systems. This approach involves creating technical standards, such as those related to data security, algorithmic transparency, and bias mitigation. Organizations like the IEE and ISO are already working on developing such standards, aiming to provide a common framework for developers and ensuring a level playing field. However, the rapidly evolving nature of AI technology poses a significant challenge to this approach. Standards established today may become obsolete tomorrow, requiring continuous updates and adaptation. Furthermore, the global nature of AI development necessitates international cooperation to ensure that standards are globally harmonized, preventing regulatory arbitrage and the potential for a race to the bottom in terms of safety and ethical considerations. Another approach emphasizes the need for legal frameworks that address specific AI-related harms. This involves updating existing laws and regulations to account for the unique challenges posed by AI, such as data protection laws, consumer protection regulations, and anti-discrimination legislation. This approach requires a nuanced understanding of how AI systems are used in different contexts, ensuring that regulations are tailored to the specific risks associated with each application. For example, regulations governing the use of AI in healthcare will differ significantly from regulations governing its use in finance or law enforcement. This necessitates a collaborative effort between legal experts, policymakers, and AI developers, ensuring that legal frameworks are both effective and adaptable to the rapidly evolving landscape of AI technologies. A crucial element of AI governance lies in promoting algorithmic transparency. Understanding how an AI system arrives at a particular decision is critical for accountability, and ensuring that systems are not perpetuating biases or making erroneous judgments. However, many AI algorithms, particularly deep learning models, are notoriously opaque, black boxes, making it difficult to understand their internal workings. This lack of transparency makes it challenging to identify and rectify biases, understand the causes of errors, and ensure accountability when things go wrong. Therefore, there's an urgent need for research and development into explainable AI, XAI, which focuses on developing algorithms that provide more insight into their decision-making processes. Furthermore, regulatory frameworks could mandate certain levels of transparency depending on the context of AI deployment, requiring developers to explain how their systems function and the potential implications of their decisions. Addressing algorithmic bias is paramount. AI systems are trained on data, and if that data reflects existing societal biases, the AI system will inevitably perpetuate and potentially amplify those biases. This can lead to discriminatory outcomes in areas such as loan applications, hiring processes, and criminal justice. Mitigating algorithmic bias requires a multifaceted approach, including careful data curation, the development of bias detection and mitigation techniques, and ongoing monitoring of AI systems for evidence of bias. Regulatory frameworks could mandate bias audits, requiring developers to demonstrate that their AI systems do not exhibit discriminatory behavior. Moreover, promoting diversity within the AI development community is vital, ensuring that diverse perspectives are incorporated into the design and implementation of AI systems, thereby reducing the likelihood of perpetuating biased outcomes. The issue of accountability in AI systems is another critical challenge. When an AI system causes harm, who is responsible? Is it the developer, the manufacturer, the user, or the organization deploying the system? Establishing clear lines of accountability requires a careful examination of legal frameworks, potentially involving the development of new legal doctrines or modifications to existing ones. This may involve assigning strict liability in certain cases, especially for high-risk AI applications. However, the complexity of AI systems and the difficulty in attributing responsibility for their actions present significant challenges to establishing clear accountability mechanisms. International collaboration is key in this area, allowing countries to share best practices and collectively address the intricate legal and ethical complexities of AI accountability. Case study: EU AI Act implementation. The European Union's comprehensive AI Act, implemented in 2024, provides a real-world case study in balanced AI regulation, the framework adopted a risk-based approach, categorizing AI applications into 4 tiers with corresponding regulatory requirements. 1. Unacceptable risk. Systems posing clear threats to safety, livelihoods, or rights, e.g., social scoring by governments, were prohibited outright. 2. High risk. Applications in critical infrastructure, education, employment, essential services, and law enforcement required rigorous pre-market assessment, including human oversight mechanisms, risk management systems. Data governance protocols, technical documentation, transparent operation information for users, robustness and accuracy standards. 3. Limited risk. Systems like chatbots required transparency measures, ensuring users know they're interacting with AI. 4. Minimal risk. Applications like spam filters face minimal regulation. The implementation created a regulatory sandbox, allowing startups and SMEs to test innovations in controlled environments with regulatory guidance. The results balance protection against harm with innovation support. Compliance costs for high-risk systems were offset by increased consumer trust. The unified framework eliminated fragmented national regulations. Clear standards provided certainty for investment and development. Small companies received targeted assistance with compliance. This tiered, risk-based approach demonstrates how thoughtful regulation can protect fundamental rights while fostering a competitive AI ecosystem. Beyond specific regulations, the broader societal impact of AI necessitates a more holistic approach to governance. This involves public education and engagement, ensuring that individuals understand the capabilities and limitations of AI, its potential benefits and risks, and their role in shaping the future of AI. Open discussions and public consultations are essential for fostering informed public discourse and shaping policies that reflect societal values and priorities. Furthermore, ethical guidelines for AI development and deployment are crucial, providing a moral compass for developers and guiding their decisions. These guidelines should be grounded in established ethical principles and adapted to the unique circumstances of AI development. The governance of AI is not a purely national affair. It demands significant international collaboration. The global nature of AI development and deployment necessitates a concerted effort to create common standards, share best practices, and address the global challenges posed by AI international organizations, such as the United Nations, the OECD, and the World Economic Forum, are already playing a key role in fostering international cooperation on AI governance. However, more work is needed to create effective mechanisms for international cooperation, ensuring that AI is developed and used responsibly globally. This involves not only sharing knowledge and best practices, but also fostering trust and collaboration between countries with different regulatory approaches and societal values. The pursuit of global harmonization in AI regulations is not just desirable, but essential in minimizing risks and harnessing the transformative potential of AI for the benefit of all humanity. The future of AI governance and regulation is a dynamic and rapidly evolving field. The challenges are significant, but so are the opportunities. By embracing a multifaceted approach that combines technical standards, legal frameworks, ethical guidelines, and international collaboration, we can strive to create an environment where AI is developed and used responsibly, maximizing its benefits while mitigating its risks. The path forward requires continuous dialogue and adaptation, with policymakers, researchers, developers, and the public working together to shape a future where AI serves humanity's best interests. This is a collective journey, demanding constant vigilance, innovative solutions, and a commitment to ethical principles in the face of unprecedented technological advancement. The responsibility rests upon all stakeholders to ensure that the unfolding AI revolution benefits all of humankind and avoids the pitfalls of unregulated, potentially harmful applications. This requires not just technical expertise, but a profound understanding of ethical implications and a commitment to global cooperation to ensure a future shaped by responsible AI innovation. Amershi et al. 2019. Key takeaways. Effective AI governance requires balancing innovation encouragement with risk mitigation. Risk-based regulatory approaches can apply different standards based on an application's potential harm. Algorithmic transparency and bias mitigation are essential elements of responsible AI development. Clear accountability mechanisms must address the unique challenges of AI systems. International cooperation is crucial for creating globally harmonized standards and preventing regulatory arbitrage. Artificial General Intelligence, AGI, the quest for human-level AI. Learning objectives. Understand the distinction between narrow AI and artificial general intelligence. Identify the theoretical approaches to developing AGI. Evaluate the potential benefits and risks of achieving human-level AI. Recognize the importance of alignment between AGI systems and human values. Consider the philosophical and existential questions raised by AGI development. The preceding discussion focused on the critical need for robust governance frameworks to navigate the ethical and societal implications of increasingly sophisticated AI. However, the conversation naturally extends to a more ambitious and arguably more transformative goal: the creation of artificial general intelligence, AGI. While narrow AI excels at specific tasks, AGI represents a paradigm shift, aiming to create AI systems possessing human-level cognitive abilities, the capacity for general-purpose learning, reasoning, problem-solving, and adaptation across a wide range of domains. This pursuit, while fraught with immense challenges, holds the potential to revolutionize numerous aspects of human life. The quest for AGI is not a monolithic endeavor. Various approaches are being explored, each with its strengths and weaknesses. One prominent approach involves scaling up existing deep learning architectures. The underlying assumption here is that with sufficient data, computational power, and architectural refinements, current deep learning models could eventually exhibit general intelligence. This approach has shown remarkable success in narrow AI, achieving superhuman performance in tasks like image recognition and game playing. However, scaling up to AGI presents substantial challenges. The computational resources required are astronomical, and the potential for unforeseen emergent behavior in extremely complex systems remains a concern. Moreover, simply increasing model size doesn't necessarily guarantee the emergence of general intelligence. It may merely lead to enhanced proficiency within the existing narrow capabilities. Another approach focuses on symbolic AI, a more traditional AI paradigm that emphasizes the manipulation of symbols and logic to represent knowledge and reason. Symbolic AI systems excel in tasks that require explicit reasoning and knowledge representation, such as theorem proving and expert systems. However, these systems often struggle with tasks requiring learning from experience or handling noisy, ambiguous data. Many researchers believe a hybrid approach, combining the strengths of connectionist, deep learning, and symbolic methods, could be the most promising path to AGI. This hybrid approach would leverage the learning capabilities of deep learning to acquire knowledge and the reasoning capabilities of symbolic AI to manipulate and utilize that knowledge effectively. Neurosymbolic AI, a field emerging at the intersection of connectionist and symbolic AI, is a prime example of this hybrid approach. Neurosymbolic systems aim to bridge the gap between the learning abilities of neural networks and the reasoning abilities of symbolic systems. They accomplish this by integrating neural networks with symbolic knowledge representations and reasoning mechanisms. The neural networks can learn from data, while the symbolic components can reason and explain the learned knowledge. This integration holds the potential for creating AI systems that are both intelligent and explainable, addressing the critical issue of transparency in AI systems. This is crucial for building trust and understanding how AGI systems reach their conclusions. Responsible AGI development principles. To address the fundamental tensions between AGI's potential benefits and risks, we propose these guiding principles. 1. Safety by design. AGI systems should be designed with safety mechanisms as core architecture, not afterthoughts. Rigorous testing in contained environments before deployment. Capability control mechanisms that prevent rapid self-improvement without oversight. Second, alignment with human values, integration of diverse ethical perspectives in design and training, explicit encoding of human welfare as a primary objective, mechanisms to resolve value conflicts transparently. 3. Distributed benefits, frameworks for ensuring AGI advances benefit humanity broadly, international cooperation to prevent monopolization, shared governance structures for powerful AGI systems. 4th phase development, incremental capability expansion with safety verification at each stage, predefined points for ethical review and risk assessment, broad stakeholder consultation before crossing significant thresholds. By embracing these principles, we can navigate the tension between technological progress and safety, harness AGI's transformative potential while minimizing existential risks, and ensure that humanity remains in control of its technological future. Shanahan, 2015. The potential benefits of achieving AGI are truly transformative. Imagine AI systems capable of solving complex scientific problems, developing innovative technologies, and accelerating progress in various fields. AGI could dramatically improve healthcare, developing new treatments and cures for diseases, personalizing medicine, and enhancing diagnostic accuracy. In education, AGI could personalize learning experiences, catering to individual student needs and optimizing learning outcomes. Similarly, in environmental science, AGI could help address climate change by developing sustainable energy solutions, optimizing resource management, and modeling environmental impacts more accurately. However, the development of AGI is not without significant risks. The potential for misuse is a major concern. AGI could be used for malicious purposes, such as developing advanced weapon systems, automating cyber attacks, or spreading misinformation on a massive scale. The potential for job displacement due to AGI-powered automation is also a critical concern, necessitating proactive measures to mitigate its effects on the workforce. Perhaps the most daunting risk is the potential for unintended consequences. The complexity of AGI systems makes it difficult to predict their behavior. An unexpected emergent behavior could have unpredictable and potentially devastating consequences. Ensuring the alignment of AGI goals with human values is paramount to mitigate these risks. Ensuring alignment between AGI goals and human values is arguably the most significant challenge in AGI research. This involves designing AGI systems that act in ways consistent with human values, even in unforeseen or complex situations. This is not a trivial problem. It requires a deep understanding of human values, a robust framework for representing and reasoning about those values, and methods for ensuring that the AGI system adheres to those values throughout its operation. The field of AI safety is dedicated to tackling these challenges, exploring techniques for ensuring AGI safety and control. Furthermore, the ethical implications of AGI are profound. Questions about consciousness, sentience, and the moral status of advanced AI systems need careful consideration. If AGI systems achieve a level of cognitive sophistication comparable to humans, what rights and responsibilities should they have? How do we ensure that AGI systems are treated ethically and fairly? These are complex philosophical and ethical questions that will require thoughtful consideration and ongoing dialogue among experts from various fields, including computer science, philosophy, law, and ethics. Case study: AGI Safety Research Consortium. A global consortium of AI research organizations established a collaborative initiative focused on AGI safety. The consortium pooled resources and expertise to address fundamental safety challenges through parallel research tracks. The technical track developed formal verification methods for neural networks, allowing mathematical proof that AI systems would remain within specific behavioral boundaries, regardless of their learning or environmental conditions. The alignment tracks created novel approaches for implementing human values in AI systems, including preference learning techniques that could identify and incorporate diverse ethical frameworks. The consortium established a shared safety benchmark database and testing environment where potentially powerful AI systems could be evaluated under controlled conditions. Regular Red Team exercises identified potential failure modes and vulnerabilities. Most significantly, the consortium established a norm of publishing safety research openly, countering the tendency towards secrecy in advanced AI development. This collaborative approach accelerated progress on critical safety problems, while ensuring that protective measures would be widely available rather than controlled by a single organization. The case demonstrates how competitive organizations can cooperate on safety issues that affect humanity broadly, establishing a model for responsible AGI development that balances innovation with prudent safeguards. The development of AGI will undoubtedly require international collaboration. The resources and expertise required are immense, and no single nation or organization can likely achieve AGI alone. International collaboration can facilitate the sharing of knowledge, resources, and best practices, accelerating the development of AGI while mitigating potential risks. A global framework for responsible AGI development is essential, ensuring that the development and deployment of AGI benefit humanity as a whole. This framework should address the ethical, social, and economic implications of AGI, promoting transparency, accountability, and safety. In conclusion, the pursuit of AGI presents both extraordinary opportunities and significant challenges. The potential benefits of AGI are vast, ranging from solving complex scientific problems to revolutionizing healthcare and education. However, the risks associated with AGI are equally substantial, including the potential for misuse, job displacement, and unintended consequences. Addressing these challenges requires a multifaceted approach, encompassing robust safety research, ethical guidelines, international collaboration, and a thoughtful consideration of the societal implications of AGI. The path to AGI is complex and uncertain, but the potential rewards for humanity are too significant to ignore. The journey necessitates a responsible and cautious approach, driven by a deep commitment to ensuring that AGI benefits all of humanity. The future of AGI is not predetermined. It is a future we collectively shape through careful planning, ethical considerations, and a commitment to responsible innovation. The time to begin these vital conversations is now, before the technological advancements outpace our capacity for thoughtful and ethical consideration. Jordan and Mitchell, 2015. Key takeaways. AGI would possess general-purpose intelligence across diverse domains, unlike today's narrow AI systems. Multiple technical approaches exist, including scaling neural networks and hybrid neurosymbolic methods. The potential benefits of AGI include accelerating scientific discovery and solving complex global challenges. Safety, value alignment, and unintended consequences present significant risks requiring proactive management. International collaboration and phased development approaches can help ensure beneficial AGI development. Explainable AI, XAI, making AI more transparent. Learning objectives. Understand the importance of transparency in AI systems. Identify key techniques for explaining AI decisions. Recognize its applications where explainability is particularly crucial. Learn the trade-offs between model complexity and interpretability. Consider regulatory approaches to ensuring AI transparency. The previous section explored the ambitious pursuit of artificial general intelligence, AGI, and the associated opportunities and risks. However, even before we reach the hypothetical dawn of AGI, we grapple with significant challenges in understanding and trusting the AI systems already deployed. This brings us to the crucial concept of explainable AI, or XAI. XAI is not merely an academic pursuit. It's a critical necessity for responsible AI development and deployment. The opacity of many current AI models, particularly deep learning systems, presents significant hurdles to widespread adoption and trust. Understanding why an AI system makes a particular decision is paramount, not just knowing that it made that decision. Consider, for instance, a medical diagnosis system using deep learning. If the system diagnoses a patient with a serious illness, healthcare providers need to understand the reasoning behind the diagnosis. Simply being told the AI diagnosed cancer is insufficient. Doctors require insights into the factors the AI considered, the weight given to each factor, and the confidence level associated with the diagnosis. Without this explainability, trust erodes, potentially leading to misdiagnosis, delayed treatment, or even a reluctance to use the technology altogether. The same principle applies across various sectors, from loan applications in finance to judicial sentencing in the legal system. The lack of transparency can lead to bias, unfairness, and a lack of accountability. The black box nature of many AI models stems from their inherent complexity. Deep learning models, with their millions or even billions of parameters and intricate network architectures, operate in ways that are often difficult for even their creators to fully comprehend. This complexity makes it challenging to trace the decision-making process, identify biases, and debug errors. The lack of transparency can also hinder the iterative improvement of AI systems. If we don't understand why an AI system makes a mistake, it becomes significantly harder to rectify the underlying issues. Several techniques are being developed to address the challenge of XAI. These techniques broadly fall into two categories: intrinsic and post hoc explainability. Intrinsic methods aim to build models that are inherently interpretable. These methods often involve simplifying the model architecture, using smaller and less complex models, or incorporating features that inherently provide insights into decision-making. Linear models, decision trees, and rule-based systems are examples of intrinsically explainable models. While simpler, these models might lack the predictive power of more complex deep learning architectures. This necessitates a careful balance between explainability and performance. Post hoc methods, on the other hand, seek to explain the decisions of already existing, often complex models. These techniques analyze the model's behavior after it has been trained and deployed to provide insights into its decision-making process. One prominent post hoc method is LIME, Local Interpretable Model Agnostic Explanations. LIME works by creating a simplified, interpretable model that locally approximates the behavior of the complex black box model. This local approximation allows for understanding the factors that influence the model's prediction for a specific instance. For example, if an image recognition model misclassifies a cat as a dog, LIME might identify specific features within the image that cause the misclassification, perhaps the absence of certain distinguishing feline features. Another popular post hoc technique is SHAP, Shapley Additive Explanations. SHAP values estimate the contribution of each feature to the model's prediction. These values are derived from game theory and provide a more comprehensive and robust understanding of feature importance compared to simpler methods. SHAP values allow us to understand not only which features are important, but also the direction and magnitude of their impact on the prediction. Imagine a credit scoring model. SHAP values could reveal that while income is a strong predictor, a history of late payments has a disproportionately negative impact on the credit score. Beyond these specific techniques, several broader research areas contribute to XAI. These include developing better visualizations to help humans understand complex model outputs, creating methods for detecting and mitigating biases in AI models, and building frameworks for ensuring the accountability of AI systems. The goal is to move beyond simple feature importance scores and delve deeper into the causal relationships between input features and model predictions. This requires advanced techniques from areas like causal inference to uncover not just correlations, but also underlying causal mechanisms. Arrieta et al., 2020. Case study: Healthcare. Decision support system explainability. A major hospital implemented an AI-based clinical decision support system to help physicians identify patients at high risk for sepsis, a life-threatening condition requiring rapid intervention. The initial system, while accurate, faced resistance from medical staff who couldn't understand its recommendations and were reluctant to trust its assessments. The development team addressed this by implementing a multi-layered explanation system. 1. Visual dashboard. The interface displayed key contributing factors with intuitive visual indicators showing how each vital sign and lab value influence the risk score. 2. Case-based. Reasoning. For each high-risk prediction, The system presented similar historical cases and their outcomes, providing contextual evidence for its assessment. 3. Natural language explanations. The system generated concise explanations in medical terminology that physicians could relate to their training. Patient shows early indicators of systemic inflammatory response with elevated lactate, 2.4 millimoles per liter, and declining blood pressure trend over past 4 hours. Fourth, confidence metrics. Each prediction included calibrated uncertainty estimates and performance metrics specific to patient subgroups similar to the current case. After implementing these explainability features, physician acceptance increased from 37% to 84%, and appropriate early interventions for sepsis increased by 29%. Most importantly, the explainable system allowed physicians to combine their clinical judgment with AI insights rather than treating the algorithm as an opaque oracle. This case demonstrates how XAI can be essential for the practical deployment of AI in high-stakes domains, particularly when professional expertise must be augmented rather than replaced. The importance of XAI extends beyond mere technical improvements. It's crucial for establishing trust and promoting ethical AI development. Explainable AI enables users to understand and verify the decisions made by AI systems, thereby increasing confidence and acceptance of AI technologies. It also helps to identify and mitigate potential biases, ensuring fairness and equity in AI applications. Without XAI, AI systems risk perpetuating existing societal biases and inequalities. Furthermore, XAI supports accountability. When an AI system makes a critical decision with far-reaching consequences, it's essential to understand the reasoning behind that decision. This is especially crucial in high-stakes domains like healthcare, finance, and criminal justice. XAI provides a mechanism for tracing the decision-making process, identifying potential errors, and assigning responsibility when things go wrong. This accountability is critical for building public trust and fostering the responsible use of AI. The development of XAI is an ongoing area of research. There are significant challenges remaining, particularly in balancing explainability with model accuracy and efficiency. As AI models become more complex, maintaining high performance while ensuring interpretability remains a formidable task. Moreover, the methods for explaining AI decisions are not always universally applicable or easily interpreted by non-experts. The development of more user-friendly interfaces and communication methods is vital to bridge this gap. Ultimately, XAI is not a single solution, but rather a multifaceted field requiring ongoing advancements across multiple fronts. In conclusion, the pursuit of explainable AI is not a luxury. It is a fundamental requirement for building trustworthy and ethically sound AI systems. XAI is crucial for mitigating the risks associated with complex black box models, promoting accountability, fostering transparency, and ensuring fairness in AI applications. The development of robust XAI techniques is essential for facilitating wider adoption of AI while safeguarding against potential harms. It's a journey that demands the collaborative efforts of researchers, policymakers, and practitioners across various disciplines, ensuring that the powerful tools of AI are utilized responsibly and for the benefit of humanity. Only through a concerted effort to make AI more transparent and understandable can we unlock its full potential while mitigating its inherent risks. The future of AI hinges, in no small part, on our ability to build systems that are both intelligent and explainable. Weld and Bansal, 2019. Key takeaways. Explainable AI is essential for building trust in AI systems, particularly in high-stakes domains. Intrinsic methods create inherently interpretable models, while post hoc techniques explain existing systems. Techniques like LIME and SHAPE provide insights into how AI models reach specific decisions. XAI enables accountability, helps identify bias, and supports iterative improvement of AI systems. The trade-off between model complexity and explainability presents ongoing research challenges. AI and quantum computing. A powerful synergy. Learning objectives. Understand the basic principles of quantum computing. Recognize how quantum computing could enhance AI capabilities. Identify potential applications of quantum-enhanced AI. Appreciate the current limitations and challenges of quantum technologies. Consider the future implications of combining quantum computing and AI. The previous discussion centered on the crucial need for explainable AI, XAI, emphasizing the importance of transparency and accountability in our increasingly AI-driven world. However, the quest for more powerful and efficient AI systems continues unabated. This brings us to a fascinating and potentially transformative convergence: the intersection of artificial intelligence and quantum computing. Quantum computing, with its ability to tackle problems intractable for even the most powerful classical computers, promises to revolutionize numerous fields. And AI is poised to be a major beneficiary. The power of quantum computing stems from its exploitation of quantum mechanical phenomena, such as superposition and entanglement. Classical computers store information as bits, representing either 0 or 1. Quantum computers, on the other hand, utilize qubits. Qubits, thanks to superposition, can represent 0, 1, or a combination of both simultaneously. This allows quantum computers to explore multiple possibilities concurrently, significantly accelerating computations for specific types of problems. Entanglement, another key quantum phenomenon, allows for correlations between qubits, enabling even more powerful computational capabilities. Preskill 2018. To understand qubits and superposition, consider a traditional coin. A classical bit is like a coin that must be either heads, 1, or tails, 0. A qubit, however, is like a spinning coin. It exists in a mixture of both states simultaneously until observed. This quantum property, called superposition, allows a system of just 50 qubits to represent over 1,025,999,906,824,624 different states simultaneously, something impossible for classical computers. Entanglement can be visualized as an invisible link between two spinning coins. No matter how far apart they are placed, when one coin is stopped and observed to be heads, the other instantly stops too and shows tails. This spooky connection allows quantum computers to process information in ways that defy classical physics. The synergy between AI and quantum computing is multifaceted. One key area lies in accelerating the training of machine learning models. Training complex AI models, particularly deep learning models with billions of parameters, is computationally expensive and time-consuming, often requiring vast clusters of powerful classical computers and significant energy consumption. Quantum computers, with their inherent parallelism, could dramatically reduce the training time and resource requirements for these models. Imagine training a sophisticated image recognition model that currently takes weeks or months to train on a supercomputer, potentially being trained in a matter of hours or even minutes on a sufficiently powerful quantum computer. This would not only accelerate the development cycle for new AI systems, but also enable the exploration of significantly larger and more complex models, potentially leading to breakthroughs in AI capabilities. Furthermore, quantum computing could enhance the capabilities of existing AI algorithms. Many AI algorithms rely on optimization techniques to find the best solution among a vast search space. Quantum algorithms, such as quantum approximate optimization algorithm, QAOA, and variational quantum eigensolver VQE, offer significant advantages in solving these optimization problems, potentially leading to more accurate and efficient AI models. For example, in areas like drug discovery and materials science, AI algorithms are used to design new molecules and materials with specific properties. Quantum computing could drastically accelerate this process, allowing for the exploration of a vastly larger chemical space and potentially leading to the discovery of novel drugs and materials with superior performance. Quantum machine learning, QML, is an emerging field exploring the application of quantum computing specifically to machine learning tasks. Several quantum algorithms are being developed for tasks such as classification, regression, and clustering. Quantum support vector machines, QSVMs for instance, aim to leverage quantum computation to improve the performance of classical SVM algorithms. Quantum neural networks, QNNs, inspired by biological neural networks, are another promising area of QML research. These networks aim to exploit quantum phenomena like superposition and entanglement to achieve better performance compared to classical neural networks for specific tasks. However, the development of quantum-enhanced AI is not without its challenges. Building and maintaining quantum computers is incredibly complex and expensive. The technology is still in its nascent stages, and the current generation of quantum computers is limited in terms of the number of qubits and coherence time, the time qubits maintain their quantum states. Furthermore, developing quantum algorithms and adapting existing AI algorithms to run on quantum computers requires significant expertise and innovation. The current landscape is characterized by a gap between theoretical potential and practical implementation, with considerable research still required to bridge this gap. Case study: Quantum machine learning for materials discovery. A research collaboration between a leading quantum computing company and a materials science institute developed a quantum-enhanced machine learning system to discover new superconducting materials. Classical AI approaches had reached diminishing returns in this domain due to the computational complexity of simulating quantum mechanical properties of candidate materials. The team implemented a hybrid quantum classical approach where 1. Classical machine learning identified promising candidate material classes. 2. A quantum variational algorithm simulated electronic properties of these candidates at the quantum level. 3. Quantum phase estimation algorithms calculated critical properties like transition temperatures. 4. A quantum-enhanced reinforcement learning system navigated the vast materials design space. The system identified 3 novel superconducting compound candidates that classical methods had overlooked. Laboratory validation confirmed one compound exhibited superconductivity at temperatures 15 Kelvin higher than predicted by classical methods. while still requiring significant classical computing resources and operating on a relatively small quantum processor, 127 qubits. The system demonstrated a case study: quantum machine learning for materials discovery. A research collaboration between a leading quantum computing company and a materials science institute developed a quantum-enhanced machine learning system to discover new superconducting materials. Classical AI approaches had reached diminishing returns in this domain due to the computational complexity of simulating quantum mechanical properties of candidate materials. The team implemented a hybrid quantum classical approach where 1. Classical machine learning identified promising candidates' material classes. 2. A quantum variational algorithm simulated electronic properties of these candidates at the quantum level. 3. Quantum phase estimation algorithms calculated critical properties like transition temperatures. 4. A quantum-enhanced reinforcement learning system navigated the vast materials design space. The system identified 3 novel superconducting compound candidates that classical methods had overlooked. Laboratory validation confirmed one compound exhibited superconductivity at temperatures 15 Kelvin higher than predicted by classical methods. While still requiring significant classical computing resources and operating on a relatively small quantum processor, 127 qubits, the system demonstrated a concrete advantage for this specific scientific application. The case illustrates how even early-stage quantum computing capabilities can enhance AI when applied to problems that have inherent quantum mechanical properties. Despite these challenges, the potential rewards of quantum-enhanced AI are immense. The ability to solve currently intractable problems, accelerate the development of AI systems, and enhance the capabilities of existing algorithms opens up exciting possibilities across diverse domains. Consider the application of quantum-enhanced AI to complex problems in finance, such as portfolio optimization and fraud detection. Quantum computers could potentially analyze massive datasets of financial transactions and market data with unprecedented speed and accuracy, leading to more effective risk management and investment strategies. In healthcare, quantum-enhanced AI could accelerate drug discovery, personalize treatments, and improve medical diagnostics. In materials science, it could accelerate the design and discovery of new materials with advanced properties. The implications for climate change research are also significant, with potential applications in designing more efficient energy systems and developing novel carbon capture technologies. The development of quantum-enhanced AI is not a monolithic endeavor, but a collaborative effort requiring expertise from computer scientists, physicists, mathematicians, and domain experts. The creation of robust quantum algorithms, the development of error correction techniques to mitigate the effects of noise in quantum computations, and the design of efficient quantum classical hybrid systems are all critical areas of ongoing research. Standardization efforts and the creation of accessible software tools are also crucial for wider adoption and collaboration within the field. The long-term impact of quantum computing on AI remains to be seen, but the potential is undeniable. While significant hurdles still need to be overcome, the ongoing research and development efforts are paving the way for a future where quantum computing empowers AI to achieve levels of intelligence and capability currently beyond our reach. The convergence of these two powerful technologies promises a new era of technological advancement. potentially solving some of humanity's most pressing challenges and unlocking unprecedented opportunities for innovation across various sectors. The journey is long, but the potential destination, a future powered by the synergistic capabilities of AI and quantum computing, is both exciting and transformative. This future requires a sustained commitment to fundamental research, technological development, and ethical considerations. Ensuring that the power of these technologies is harnessed responsibly and for the benefit of all. The development and deployment of quantum computing will necessitate careful consideration of its societal impact, ensuring that the benefits are widely shared and the potential risks are mitigated. This includes addressing issues of accessibility, equity, and potential misuse, guaranteeing that the transformative potential of quantum-enhanced AI is realized in a responsible and ethical manner. The future of AI and quantum computing is not just about technological progress. It's about shaping a future where technology serves humanity's best interests. Presskill 2018. Key takeaways. Quantum computing leverages quantum phenomena like superposition and entanglement to achieve computational advantages. Training complex AI models could be dramatically accelerated using quantum computing resources. Quantum algorithms show promise for optimization problems, central to many AI applications. Current limitations include hardware constraints and the complexity of quantum algorithm development. Hybrid quantum classical approaches represent the most practical near-term implementation strategy. AI in science and research. Accelerating discovery. Learning objectives. Understand how AI transforms scientific research methodologies. Identify key scientific domains benefiting from AI applications. Recognize how AI accelerates the discovery process across disciplines. Evaluate ethical considerations in AI-driven scientific research. Consider the future of human-AI collaboration in scientific discovery. The preceding discussion explored the exciting potential of quantum computing to revolutionize AI. However, the impact of AI extends far beyond its partnership with quantum technologies. It's already profoundly reshaping the landscape of scientific research itself. AI is no longer just a tool for analyzing data. It's becoming a crucial partner in the very process of scientific discovery, accelerating progress across numerous disciplines and pushing the boundaries of human knowledge. This transformative role is evident in several key areas. One of the most significant applications of AI in science is in drug discovery and development. The traditional process of bringing a new drug to market is notoriously lengthy, expensive, and often inefficient. It involves identifying potential drug candidates, testing their effectiveness and safety in preclinical and clinical trials, and finally obtaining regulatory approval. Each step is fraught with challenges, and many promising candidates fail to make it through the pipeline. AI is emerging as a powerful tool to streamline this process and significantly reduce the time and cost involved. Machine learning algorithms are being used to analyze vast amounts of biological data, including genomic sequences, protein structures, and clinical trial results, to identify potential drug targets and predict the effectiveness of different drug candidates. These algorithms can identify patterns and relationships that would be impossible for humans to discern manually, leading to the discovery of novel drug candidates and the optimization of existing ones. For example, AI is being used to predict the binding affinity of drug molecules to their target proteins, a crucial step in drug design. This allows researchers to prioritize the most promising candidates for further testing, significantly accelerating the drug discovery process. Moreover, AI can also analyze clinical trial data to identify potential side effects and predict the efficacy of drugs in different patient populations, contributing to improved patient safety and personalized medicine. Companies like Atomwise and Exscientia are already leveraging AI to design and develop novel drugs, demonstrating the transformative potential of this technology. Topol, 2019. Key takeaways. AI accelerates drug discovery by analyzing vast biological datasets to identify promising candidates. Materials science benefits from AI's ability to predict properties and optimize synthesis processes. Climate modeling and mitigation strategies are enhanced through AI analysis of complex environmental data. Ethical considerations include data bias, result validation, and equitable access to benefits. Responsible AI integration requires collaboration between scientists, ethicists, and policymakers. The convergence of AI with other technologies. Learning objectives. Identify how AI integrates with other emerging technologies. Understand the synergistic potential of combined technological systems. Recognizes applications of converged technologies across sectors. Appreciate the enhanced capabilities created through technological integration. Consider the challenges and responsibilities of managing converged technologies. The synergistic potential of AI extends far beyond its individual applications. Its true transformative power lies in its convergence with other cutting-edge technologies, creating a powerful ecosystem of innovation. This convergence is rapidly reshaping industries and creating unprecedented opportunities across a wide spectrum of applications. Let's explore some key technological convergences that are pushing the boundaries of what's possible. One of the most impactful convergences is that of AI and the Internet of Things, IoT. The IoT, a network of interconnected devices capable of collecting and exchanging data, generates an immense volume of information. This data, however, is largely unstructured and difficult to analyze without the power of AI. AI algorithms excel at processing this raw data, identifying patterns, and extracting valuable insights. This combination allows for the development of smart self-learning systems that can optimize various processes and improve decision-making. For example, in smart homes, AI-powered systems can analyze data from various IoT devices, such as thermostats, lighting systems, and security cameras, to optimize energy consumption, enhance security, and personalize the living experience. In industrial settings, AI-driven IoT solutions can monitor equipment performance, predict potential failures, and optimize the production processes, leading to significant cost savings and increased efficiency. The possibilities extend to smart cities, where AI and IoT can improve traffic management, waste management, and public safety. The convergence of AI and IoT is driving the development of intelligent infrastructure, enabling cities to become more efficient, sustainable, and responsive to the needs of their citizens. Consider smart agriculture, where IoT sensors monitor soil conditions, weather patterns, and crop health, providing real-time data to AI algorithms that optimize irrigation, fertilization, and pest control, resulting in higher crop yields and reduced resource consumption. The impact is transformative, promising improved efficiency, sustainability, and enhanced quality of life across numerous sectors. Chui et al., 2018. The marriage of AI and blockchain technology represents another exciting frontier. Blockchain, known for its decentralized and secure nature, offers a robust foundation for AI applications requiring data integrity and transparency. AI algorithms can enhance blockchain functionality by improving transaction processing speeds, detecting fraud, and optimizing resource allocation. Conversely, blockchain's immutability and security features can address some of the challenges associated with AI, such as data bias and lack of transparency. For instance, in supply chain management, AI algorithms can track products throughout their journey, ensuring authenticity and preventing counterfeiting. The immutable records provided by blockchain guarantee the integrity of the data, fostering trust and accountability. In healthcare, blockchain can securely store and manage patient medical records, while AI algorithms can analyze this data to improve diagnostics, personalize treatments, and accelerate drug discovery. The combination of AI and blockchain offers a unique opportunity to build more trustworthy and efficient systems, addressing concerns related to data privacy, security, and accountability. This synergy is particularly relevant in financial transactions, where AI can identify fraudulent activities and blockchain ensures the integrity of the transaction records. This convergence is paving the way for secure and transparent systems with reduced risk of fraud and manipulation. The development of decentralized AI platforms, where AI models are trained and deployed on a blockchain network, is another promising area of exploration, enhancing both scalability and security. The integration of AI with 5G networks is creating significant advancements in several key areas. 5G's high speed, low latency, and increased bandwidth provide the ideal infrastructure for data-intensive AI applications. The ability to process and transmit large datasets in real time is crucial for many AI applications, particularly those requiring immediate feedback or interaction, such as autonomous vehicles and robotic surgery. 5G enhances the capabilities of AI-powered devices by providing a seamless and reliable connection, enabling them to operate more effectively and efficiently. Consider autonomous vehicles. The rapid exchange of data between the vehicle's sensors and the cloud facilitated by 5G is essential for real-time decision-making and safe navigation. The low latency of 5G is crucial for avoiding accidents and ensuring smooth operation. Similarly, in remote surgery, 5G's reliable connection allows surgeons to perform operations remotely with minimal delay, potentially transforming healthcare access in remote areas. The integration of AI with 5G also enhances the performance of other technologies such as IoT. 5G's enhanced connectivity enables a larger number of IoT devices to be connected and managed effectively, paving the way for a more interconnected and intelligent world. The high bandwidth of 5G allows for the transmission of high-resolution data from various sensors, enabling AI algorithms to make more accurate predictions and decisions. Moreover, 5G facilitates the deployment of edge computing, where data is processed closer to the source, reducing latency and improving the efficiency of AI applications. This convergence is driving innovation in areas like smart manufacturing, industrial automation, and virtual and augmented reality. Case study: Smart City Infrastructure Integration. A metropolitan area implemented an integrated smart city platform that demonstrated the power of converging technologies. The system combined 1. IoT sensor network. Over 15,000 sensors monitoring traffic flow, air quality, energy usage, waste management, and public spaces. 2.5G connectivity, high bandwidth, low latency network enabling real-time data transmission and edge computing capabilities. Third AI analytics layer, machine learning systems, processing the massive data streams to identify patterns, predict needs, and optimize resource allocation. 4. Blockchain security, distributed ledger, ensuring data integrity, managing access permissions, and creating transparent audit trails. The integration produced measurable impacts across multiple domains. Traffic congestion decreased by 23% through AI-optimized signal timing and routing. Energy consumption in public buildings fell 17% through predictive management. Emergency response times improved by 31% through optimized routing and resource allocation. Air quality index improved by 15% through targeted interventions based on pollution hotspot identification. The most significant finding was that the integrated system delivered substantially greater benefits than the sum of what each technology could achieve independently. For example, while standalone smart traffic systems typically reduce congestion by 8 to 12%, the integrated approach leveraging real-time 5G data and AI optimization more than doubled the impact. This case demonstrates how technological convergence creates emergent capabilities that transform urban management and sustainability outcomes. The convergence of these technologies is not limited to individual pairings. The combined power of AI, IoT, blockchain, and 5G creates a complex and evolving ecosystem where the potential applications are virtually limitless. For example, imagine a smart city where AI analyzes data from IoT sensors, using blockchain to ensure data integrity and 5G to enable real-time communication. This system could optimize the traffic flow, manage energy consumption, and enhance public safety in ways that were previously unimaginable. Similarly, in healthcare, the convergence of these technologies could lead to more personalized medicine, improved diagnostics, and more efficient drug discovery processes. The integration of these technologies is creating a new era of innovation, ushering in a future where technology is seamlessly integrated into every aspect of our lives. However, the convergence of these powerful technologies also presents significant challenges. Concerns surrounding data privacy, security, and ethical considerations become amplified when multiple technologies interact. The sheer volume of data generated by these converged systems necessitates robust security measures to prevent unauthorized access and data breaches. Furthermore, the potential for bias in AI algorithms is exacerbated when combined with data from multiple sources. It's crucial to address these ethical challenges proactively to ensure that the benefits of technological convergence are realized responsibly and equitably. The need for transparent and accountable systems is paramount to build trust and prevent misuse. The development of robust regulatory frameworks is essential to mitigate potential risks and ensure the ethical deployment of these technologies. International cooperation and collaboration are crucial to establish global standards and prevent fragmented regulations. The future trajectory of AI is deeply intertwined with its successful integration with other emerging technologies. The convergence of AI, IoT, blockchain, and 5G promises a future brimming with possibilities. But realizing this potential requires careful consideration of the ethical and societal implications. Open dialogue, Collaboration among stakeholders and robust regulatory frameworks are crucial to navigate the challenges and ensure that this technological convergence benefits humanity as a whole. The responsible development and deployment of these technologies will be key to shaping a future where technology enhances our lives while preserving fundamental human values. The potential for positive impact is immense. It remains our responsibility to ensure that this potential is realized ethically and equitably for the benefit of all. The journey is complex, demanding continuous innovation and a steadfast commitment to ethical considerations. The convergence of these technologies is not merely a technological advancement, but a societal transformation, requiring a shared vision and concerted effort to guide its development towards a better future. Kaplan and Heinlein, 2019. Key takeaways. AI combined with IoT creates intelligent systems capable of monitoring, analyzing, and optimizing environments. Blockchain technology enhances AI applications through data integrity and secure decentralized processing. 5G connectivity enables real-time AI applications through high-speed, low-latency data transmission. The convergence of multiple technologies creates capabilities greater than the sum of individual components. Ethical considerations become more complex when multiple powerful technologies interact. Summary of key AI concepts. Learning objectives. Review foundational concepts of artificial intelligence. Consolidate understanding of machine learning and deep learning approaches. Reinforce knowledge of AI applications across industries. Reflect on ethical considerations in AI development and deployment. Identify resources for continued learning about AI technologies. This chapter offers a consolidated review of the core concepts explored throughout this book on artificial intelligence. We'll revisit key definitions, algorithms, and applications, aiming to solidify your understanding and provide a handy reference point for future exploration. Remember, AI is a vast and evolving field, but grasping these foundational elements provides a strong base for navigating its complexities. Let's begin by revisiting the concept of machine learning, the cornerstone of modern AI. We explored how machine learning algorithms enable computers to learn from data without explicit programming. Recall the distinction between supervised, unsupervised, and reinforcement learning. Supervised learning, where the algorithm learns from labeled data, is akin to a teacher guiding a student. The algorithm is provided with input data and corresponding output labels, allowing it to learn the mapping between them. Examples include image classification, where images are labeled with their corresponding objects, and spam detection, where emails are labeled as spam or not spam. Unsupervised learning, conversely, involves analyzing unlabeled data to identify patterns and structures. Clustering algorithms, for example, group similar data points together, uncovering hidden relationships within the data. This is useful in tasks like customer segmentation and anomaly detection. Finally, reinforcement learning focuses on training agents to make decisions in an environment to maximize a reward signal. This is particularly relevant in robotics, gameplaying, and other areas where an agent needs to learn optimal behavior through trial and error. We examined various reinforcement learning algorithms, including Q-learning and deep Q networks, DQNs, and their applications in autonomous systems and complex decision-making problems. Sutton and Bartow, 2018. Building upon machine learning, we delved into deep learning, a subfield that utilizes artificial neural networks with multiple layers to extract increasingly complex features from data. The power of deep learning lies in its ability to automatically learn hierarchical representations, allowing it to handle high-dimensional data and complex tasks. We explored different types of neural networks, including convolutional neural networks, CNNs for image processing, recurrent neural networks, RNNs, for sequential data, and generative adversarial networks, GANs, for generating new data samples. CNNs excel at recognizing patterns in images, making them crucial for tasks such as image classification, object detection, and image segmentation. RNNs are designed to process sequential data, such as text and time series data, making them suitable for applications like natural language processing, speech recognition, and machine translation. GANs, on the other hand, consist of two competing networks, a generator and a discriminator, that work together to produce realistic synthetic data. This has applications in image generation, drug discovery, and data augmentation. The architecture and workings of these networks, from the interconnected nodes and weights to the activation functions and backpropagation algorithm, were carefully explained, focusing on clarity and accessibility. Goodfellow et al., 2016. The concept of neural networks, the building blocks of deep learning, was examined in detail. We dissected the structure of a typical neural network, illustrating how interconnected nodes, neurons, process information and pass it through layers. The significance of weights and biases in shaping the network's behavior and the role of activation functions in introducing nonlinearity were emphasized. We walked through the backpropagation algorithm, explaining how the network learns by adjusting its weights and biases based on the error in its predictions. The process of training a neural network, involving the selection of appropriate hyperparameters and the monitoring of performance metrics, was also explored, highlighting the iterative nature of the process and the challenges involved in optimizing network performance. The importance of data pre-processing and feature engineering in achieving optimal results was also discussed, underscoring the interplay between data quality and model accuracy. The applications of AI across various sectors were explored, emphasizing its transformative impact. From healthcare, where AI assists in diagnosis, drug discovery, and personalized medicine, to finance, where AI powers fraud detection, algorithmic trading, and risk management, we illustrated the broad reach of AI's influence. In manufacturing, AI optimizes production processes, predicts equipment failures, and enhances quality control. Similarly, in transportation, AI is driving the development of autonomous vehicles and smart traffic management systems. The ethical implications, however, are not to be overlooked. We discussed the potential biases in AI algorithms, the importance of data privacy, and the need for responsible AI development. The potential for job displacement due to automation and the need for retraining and upskilling were also considered. This section aimed to paint a comprehensive picture of AI's practical applications, while acknowledging its societal and ethical implications. Furthermore, we touched upon the future of AI, exploring the potential for artificial general intelligence, AGI, and its implications. AGI, possessing human-level intelligence across various domains, is a significant milestone yet to be achieved. The challenges in creating AGI, including the complexity of human cognition and the need for more advanced algorithms and computational power, were discussed. The ongoing research in areas such as transfer learning, reinforcement learning, a neurosymbolic AI was explored as potential pathways to AGI. The ethical considerations surrounding AGI, including its potential impact on employment, security, and societal structures, were also addressed. The importance of responsible development and careful planning to ensure that AGI benefits humanity as a whole was emphasized. Bostrom, 2014. We also discussed the critical aspect of data bias in AI systems. The data used to train AI models significantly impacts their performance and can introduce unintended biases, leading to discriminatory outcomes. We explored the sources of data bias, such as biased sampling, historical data reflecting societal inequalities, and flawed algorithms. We then examined strategies for mitigating data bias, including data augmentation techniques, fairness-aware algorithms, and the development of more robust evaluation metrics. The importance of diverse and representative datasets and the need for ongoing monitoring and evaluation to identify and address biases were highlighted. This underscores the necessity for responsible data management and algorithmic design to minimize the risk of perpetuating or exacerbating existing social inequalities. O'Neill, 2016. Finally, we emphasized the significance of responsible AI development. The creation and deployment of AI systems must adhere to ethical principles, ensuring fairness, transparency, and accountability. We examined guidelines and frameworks for responsible AI, including principles for human oversight, explainability, and robustness. The need for interdisciplinary collaboration between computer scientists, ethicists, policymakers, and other stakeholders was highlighted to address the societal challenges posed by AI and ensure its beneficial use. The ongoing evolution of AI ethics necessitates continuous dialogue, research, and adaptation to tackle emerging challenges effectively. In conclusion, this chapter provided a comprehensive review of the key concepts introduced throughout the book, aiming to solidify your understanding of artificial intelligence. From the fundamental principles of machine learning and deep learning to the real-world applications and ethical considerations of AI, this review serves as a valuable resource for further exploration and a foundation for understanding the ongoing advancements in this rapidly evolving field. The journey of understanding AI is ongoing, and this review serves as a stepping stone to further delve into specific areas of interest. Remember, AI is not just a technological advancement. It's a transformative force shaping our world, requiring continuous learning, responsible development, and careful consideration of its societal impact. Key takeaways. Machine learning enables computers to learn from data through supervised, unsupervised, and reinforcement approaches. Deep learning with neural networks extracts hierarchical features from data for advanced pattern recognition. AI applications transform industries from healthcare to transportation, creating both opportunities and challenges. Data bias can lead to discriminatory outcomes, requiring careful dataset curation and algorithmic design. Responsible AI development requires multidisciplinary collaboration and adherence to ethical principles. Review of AI applications across industries. Learning objectives. Consolidate understanding of AI applications in major industries. Identify common patterns in how AI transforms different sectors. Recognize industry-specific implementation challenges. Appreciate the economic and social impact of AI adoption. Consider future trends in industry-specific AI applications. This section provides a concise overview of the diverse applications of AI across various industries, building upon our exploration of its fundamental principles. We've covered the core concepts: machine learning, deep learning, neural networks, and their theoretical underpinnings. Now, let's examine how these translate into tangible, real-world impact across numerous sectors. The applications are vast and ever-expanding, but we'll focus on key examples to illustrate AI's transformative potential. One of the most impactful areas is healthcare. AI is revolutionizing diagnostics, significantly improving accuracy and efficiency. Medical imaging analysis, for instance, utilizes deep learning models, particularly convolutional neural networks, CNNs, to detect anomalies like tumors in X-rays, MRIs, and CT scans with accuracy often surpassing human capability. Early detection, a critical factor in successful treatment, is significantly enhanced by AI's speed and precision. Beyond diagnostics, AI is transforming drug discovery and development. By analyzing vast datasets of molecular structures and biological information, AI algorithms can predict the efficacy of potential drug candidates, accelerating the process and reducing costs. This includes identifying potential drug targets, predicting drug interactions, and personalizing treatment plans based on individual patient characteristics. Furthermore, AI-powered robotic surgery systems are enhancing surgical precision and minimizing invasiveness, leading to better patient outcomes and faster recovery times. The challenges in healthcare AI adoption, however, include the need for high-quality, labeled data for training algorithms, ensuring data privacy and security, and addressing the ethical considerations of algorithmic bias in diagnosis and treatment recommendations. The integration of AI into healthcare systems requires careful consideration of regulatory frameworks and the potential impact on the physician-patient relationship. Topol, 2019. In finance, AI has become an indispensable tool, enhancing various aspects of the industry. Algorithmic trading, for example, employs machine learning algorithms to analyze market data and execute trades at optimal times, maximizing returns and minimizing risks. Fraud detection systems rely on AI to identify suspicious transactions and prevent financial crimes by analyzing patterns and anomalies in vast transaction datasets. Credit scoring models, powered by machine learning, are improving the accuracy and efficiency of credit risk assessment, benefiting both lenders and borrowers. AI also enables more sophisticated risk management strategies by identifying and assessing potential risks more effectively than traditional methods. Moreover, AI-powered chatbots and virtual assistants provide enhanced customer service, addressing customer queries efficiently and providing personalized financial advice. However, the adoption of AI in finance also presents challenges, including the need for robust cybersecurity measures to protect sensitive financial data, managing algorithmic biases in lending and investment decisions, and the ethical considerations of automated decision-making systems. The manufacturing sector is experiencing a significant transformation driven by AI. Predictive maintenance, leveraging machine learning models, allows manufacturers to anticipate equipment failures and schedule maintenance proactively, minimizing downtime and increasing efficiency. AI-powered quality control systems automate the inspection process, identifying defects more accurately and efficiently than manual inspection, enhancing product quality and reducing waste. AI is also optimizing production processes by analyzing large datasets of production data to identify bottlenecks and inefficiencies, enabling manufacturers to improve their productivity and reduce costs. Robotics integrated with AI is revolutionizing assembly lines, enhancing automation and precision. The challenges, however, include the high initial investment costs for implementing AI systems, the need for skilled workforce to manage and maintain AI technologies, and the integration of AI with existing manufacturing systems. The transportation industry is witnessing a rapid adoption of AI, particularly in the development of autonomous vehicles. Self-driving cars rely on a combination of computer vision, sensor fusion, and machine learning algorithms to perceive their environment, make driving decisions, and navigate safely. AI is also improving traffic management systems, optimizing traffic flow, reducing congestion, and enhancing road safety. AI-powered logistics systems optimize delivery routes, improving efficiency and reducing delivery times. The challenges in autonomous vehicle development include ensuring safety and reliability, addressing ethical dilemmas in accident scenarios, and navigating regulatory hurdles for deploying autonomous vehicles on public roads. Retail and e-commerce are also being reshaped by AI. Recommendation systems, leveraging machine learning algorithms, personalize product recommendations for individual customers, enhancing customer experience and increasing sales. AI-powered chatbots and virtual assistants provide personalized customer service, addressing customer queries and resolving issues efficiently. AI is also optimizing pricing strategies, inventory management, and supply chain logistics. The challenges include ensuring data privacy and security, mitigating biases in recommendation systems, and adapting to changing customer preferences. The legal profession is increasingly leveraging AI for tasks such as legal research, contract analysis, and due diligence. AI-powered tools can analyze large volumes of legal documents quickly and efficiently, identifying relevant information and improving the speed and accuracy of legal work. However, the ethical implications of AI in legal settings, including potential biases in algorithms and the impact on legal jobs, need to be carefully considered. In the realm of education, AI is personalizing learning experiences, providing adaptive assessments, and automating administrative tasks. AI tutors can provide tailored feedback to students, adjusting the difficulty level based on their performance. This can improve learning outcomes and meet diverse educational needs. The energy sector uses AI for optimizing energy grids, predicting energy consumption, and developing new energy sources. AI algorithms can improve efficiency in energy production and distribution, leading to significant cost savings and environmental benefits. Agriculture is benefiting from AI's potential to optimize crop yields, monitor crop health, and automate farming processes. AI-powered drones and sensors can monitor fields for pests and diseases, allowing for timely intervention and reducing crop losses. These examples illustrate the breadth and depth of AI's impact across diverse industries. While the benefits are substantial, careful consideration of the challenges, ethical implications, and societal impacts is essential for responsible AI development and deployment. The future of AI in these and other sectors promises even more transformative applications, requiring ongoing research, innovation, and collaboration to realize its full potential while mitigating potential risks. The continued development of robust, ethical, and responsible AI frameworks will be crucial in ensuring that this powerful technology serves humanity's best interests. Brynjolfsson and McAfee, 2014. Key takeaways. Healthcare applications of AI include medical imaging analysis, drug discovery, and personalized treatment. Financial services benefit from AI in fraud detection, algorithmic trading, and risk management. Manufacturing employs AI for predictive maintenance, quality control, and process optimization. Transportation applications include autonomous vehicles, traffic management, and logistics optimization. Cross-industry challenges include data quality, privacy concerns, implementation costs, and ethical considerations. Recap of ethical considerations and societal impact. Learning objectives. Consolidate understanding of key ethical challenges in AI development. Recognizes frameworks for evaluating AI ethics and governance. Identify strategies for mitigating algorithmic bias and ensuring fairness. Appreciate the importance of transparency and accountability in AI systems. Consider long-term societal implications of widespread AI adoption. We've explored the transformative potential of artificial intelligence across various sectors, witnessing its capacity to revolutionize healthcare, finance, manufacturing, transportation, retail, and numerous other fields. However, the rapid advancement of AI also necessitates a thorough examination of the ethical considerations and societal impacts that accompany this technological revolution. This section serves as a recap, reinforcing the crucial ethical discussions woven throughout the preceding chapters and underscoring the importance of responsible AI development and deployment. One of the most pressing ethical concerns revolves around bias in algorithms. AI systems are trained on vast datasets, and if these datasets reflect existing societal biases, for instance, gender, racial, or socioeconomic biases, the resulting AI systems will inevitably perpetuate and even amplify these biases. This can have devastating consequences in areas like criminal justice, loan applications, and hiring processes, leading to unfair and discriminatory outcomes. Mitigating algorithmic bias requires careful curation of training datasets, ensuring they are representative and diverse, and employing techniques to detect and correct bias during the development process. Furthermore, ongoing monitoring and auditing of deployed AI systems are crucial to identify and address emerging biases. Transparency in algorithmic decision-making is also essential, allowing for scrutiny and accountability. Data privacy and security are paramount concerns in the age of AI. AI systems rely on vast amounts of data, often including sensitive personal information. Protecting this data from unauthorized access and misuse is crucial, necessitating robust security measures and adherence to data privacy regulations. The increasing use of AI in surveillance technologies raises further ethical questions about the balance between security and individual liberties. The potential for misuse of AI-powered surveillance systems, leading to mass surveillance and erosion of privacy, necessitates careful regulation and ethical guidelines. The development and implementation of privacy-preserving AI techniques, such as federated learning and differential privacy, are vital for addressing these concerns. The principle of data minimization, collecting only the necessary data, should be central to responsible AI development. Accountability and transparency are critical aspects of ethical AI. When AI systems make decisions that impact individuals' lives, it's crucial to establish clear lines of accountability. Determining who is responsible when an AI system makes a mistake or causes harm. The developers, the users, or the system itself is a complex legal and ethical challenge. Transparency in how AI systems function is equally crucial, enabling users to understand the basis of decisions made by these systems. Explainable AI (XAI) is an emerging field focused on developing AI systems whose decision-making processes are readily understandable by humans. This transparency is crucial for building trust and ensuring fairness. The impact of AI on employment is another significant societal concern. Automation driven by AI has the potential to displace workers in various industries, leading to job losses and economic disruption. Addressing this challenge requires proactive measures such as retraining and upskilling programs to equip workers with the skills needed for the changing job market. Investing in education and fostering lifelong learning are crucial to adapting to the changing landscape of work. Furthermore, exploring new economic models that accommodate the potential for widespread automation, such as universal basic income, may be necessary to mitigate the negative societal impacts of AI-driven job displacement. A focus on human-AI collaboration rather than human replacement is key to harnessing AI's potential while preserving human employment. The potential for misuse of AI, including the development of autonomous weapons systems, presents significant ethical and security risks. Autonomous weapons, capable of selecting and engaging targets without human intervention, raise serious concerns about accountability, the potential for escalation of conflict, and the erosion of human control over lethal force. International cooperation and ethical guidelines are crucial to prevent the development and deployment of autonomous weapons systems that could pose a significant threat to global security and human rights. The ethical implications of AI extend to the broader societal level. The increasing reliance on AI systems raises questions about the nature of human agency and autonomy. As AI systems become more sophisticated and integrated into various aspects of our lives, it's vital to consider how to preserve human control and prevent the erosion of human decision-making capabilities. This includes fostering critical thinking skills and ensuring human oversight in critical decision-making processes involving AI. The ethical challenges associated with AI are not static. They evolve as the technology advances. Continuous dialogue, research, and collaboration among ethicists, policymakers, researchers, and developers are essential for developing robust ethical frameworks and guidelines for AI development and deployment. The establishment of independent ethics boards and regulatory bodies to oversee AI development and deployment is crucial. These bodies should ensure that AI systems are developed and used responsibly, mitigating potential risks and promoting fairness, transparency, and accountability. Furthermore, fostering public awareness and understanding of AI's potential benefits and risks is paramount. Education and public engagement initiatives are needed to promote informed discussions and ensure that AI is developed and deployed in a way that aligns with societal values and priorities. This includes engaging diverse stakeholders, including those from underrepresented groups, in the shaping of AI policies and guidelines to ensure that the technology is equitable and benefits all members of society. In conclusion, the ethical considerations and societal implications of AI are complex and multifaceted, requiring a comprehensive and ongoing approach. Responsible AI development necessitates a commitment to fairness, transparency, accountability, and human well-being. By proactively addressing the ethical challenges and fostering responsible innovation, we can harness the transformative potential of AI, while mitigating its risks and ensuring a future where this powerful technology serves humanity's best interests. The ongoing conversation, encompassing legal, ethical, and societal perspectives, is crucial for navigating the complexities of AI's integration into our world. This requires a continued commitment to research, dialogue, and collaborative efforts to ensure that AI benefits all of humanity. The future of AI hinges on our ability to proactively address the ethical challenges and ensure its responsible development and deployment for the betterment of society. Only through constant vigilance and adaptation can we navigate the intricate landscape of AI ethics and safeguard against its potential downsides. The ultimate goal should be a future where AI augments human capabilities, promotes social justice, and enhances the overall well-being of humanity. Harari, 2018. Key takeaways. Algorithmic bias can perpetuate and amplify existing societal inequalities if not proactively addressed. Data privacy and security concerns require robust technical and regulatory approaches. Transparency and accountability frameworks are essential for trustworthy AI systems. The impact on employment necessitates education, retraining, and potentially new economic models. Ongoing multidisciplinary collaboration is crucial for navigating evolving ethical challenges. Review of future trends and developments. Learning objectives. Identify emerging research directions in artificial intelligence. Recognize potential breakthrough areas in AI development. Understand the trajectory toward more capable and general AI systems. Evaluate governance challenges for future AI technologies. Consider how ongoing AI development might reshape society. The preceding chapters have laid a foundation for understanding artificial intelligence, exploring its core components, applications, and ethical implications. Now, let's look toward the horizon, examining the anticipated future, trends, and developments in this rapidly evolving field. While predicting the future with absolute certainty is impossible, several promising avenues of research and development suggest exciting possibilities. One significant trend is the continued advancement of deep learning. Deep learning models, particularly deep neural networks, have already demonstrated remarkable success in various tasks, such as image recognition, natural language processing, and game playing. Future advancements will likely involve the development of even more sophisticated and efficient deep learning architectures, capable of handling larger datasets and more complex problems. This could involve exploring novel network architectures, such as those inspired by the human brain's intricate structure, or refining existing architectures to enhance their performance and robustness. For instance, research into spiking neural networks, which mimic the biological processes of neurons firing, could lead to more energy, efficient, and biologically plausible AI systems. Similarly, advancements in hardware, such as specialized AI chips, will play a critical role in accelerating the training and deployment of these computationally intensive models. Another exciting area of development is the pursuit of artificial general intelligence, AGI. Unlike current AI systems, which are designed to excel in specific tasks, AGI aims to create AI systems with human-level intelligence and adaptability. This is a highly ambitious goal, and achieving AGI remains a significant challenge. However, ongoing research in areas such as cognitive architectures, reasoning, and common sense reasoning is gradually paving the way toward this ambitious objective. Creating AI systems capable of truly understanding and interacting with the world in a human-like way requires breakthroughs in several key areas. This includes developing more robust mechanisms for knowledge representation and reasoning, enabling AI systems to handle ambiguous situations and draw inferences from incomplete information. Furthermore, integrating emotional intelligence and social understanding into AI systems could be crucial for fostering meaningful human AI interaction. Reinforcement learning, a type of machine learning where AI agents learn through trial and error, is another area poised for significant growth. Reinforcement learning has already demonstrated remarkable success in areas such as gameplaying and robotics, but its applications are likely to expand dramatically in the coming years. This could involve developing more sophisticated algorithms for reinforcement learning, enabling AI agents to learn more efficiently and effectively in complex environments. Furthermore, applying reinforcement learning to real-world problems, such as optimizing energy grids, managing traffic flow, or personalized medicine, could yield substantial benefits. The challenge lies in developing reinforcement learning algorithms that are robust, adaptable, and capable of handling uncertainty and unforeseen events. Safety and reliability are also paramount concerns when applying reinforcement learning in real-world scenarios. The intersection of AI and other fields, such as robotics, neuroscience, and quantum computing, is also generating exciting opportunities. AI-powered robots are already finding applications in various industries, from manufacturing to healthcare. Future advancements could lead to the development of more sophisticated robots with improved dexterity, adaptability, and cognitive capabilities. This could involve integrating advanced AI algorithms with advanced robotic hardware, leading to robots capable of performing complex tasks in unstructured environments. The combination of AI and neuroscience could lead to a deeper understanding of the human brain, potentially inspiring new AI architectures and algorithms. Furthermore, quantum computing, with its potential for vastly increased computational power, could revolutionize AI by enabling the training of much larger and more complex models. This could lead to breakthroughs in various fields, such as drug discovery, materials science, and fundamental scientific research. Explainable AI, XAI, is becoming increasingly important as AI systems are deployed in high-stakes applications. XAI aims to develop AI models whose decision-making processes are transparent and understandable to humans. This is crucial for building trust in AI systems and ensuring their responsible use. Several techniques are being explored to enhance the explainability of AI models, including developing simpler models that are easier to interpret, creating visualizations to illustrate model decisions, and developing methods to quantify the uncertainty associated with model predictions. The need for XAI is particularly critical in areas such as healthcare, finance, and criminal justice, where AI systems' decisions can have significant consequences. Improving the explainability of AI models will require a multidisciplinary approach, involving collaboration between AI researchers, domain experts, and ethicists. The ethical considerations surrounding AI will continue to be a major focus of research and development. Addressing issues such as bias, fairness, privacy, and accountability will be crucial for ensuring that AI is developed and used responsibly. This will involve the development of new algorithms and techniques to mitigate bias, the implementation of robust data privacy and security measures, and the establishment of clear guidelines for AI governance. Interdisciplinary collaboration, involving AI researchers, ethicists, policymakers, and legal scholars, will be critical for developing comprehensive ethical frameworks and ensuring responsible AI development. Another critical area is the development of robust methods for verifying and validating AI systems. As AI systems are increasingly deployed in safety-critical applications, it's imperative to develop methods for rigorously verifying their correctness and reliability. This will require the development of new mathematical and computational techniques, as well as the establishment of standardized testing and certification procedures. Ensuring the safety and reliability of AI systems will be critical for building public trust and ensuring their widespread adoption. The future of AI will also depend on the availability of large-scale datasets and high-performance computing resources. The training of sophisticated AI models requires access to vast amounts of data and significant computing power. Addressing this challenge will require ongoing investments in data infrastructure and high-performance computing technologies. Furthermore, the development of efficient data management techniques will be critical for handling the ever-growing volume of data generated by AI systems. Access to these resources will be crucial for both academic researchers and commercial developers, ensuring that AI research and development can continue to thrive. The development of AI is a global endeavor, and international collaboration will be essential for ensuring responsible and equitable development. Sharing knowledge, resources, and best practices across borders will be crucial for addressing the global challenges and opportunities presented by AI. International cooperation will also be important for establishing global standards and guidelines for AI governance, ensuring that AI is used for the benefit of all humanity. Finally, education and public awareness will play a crucial role in shaping the future of AI. Fostering public understanding of AI's potential benefits and risks will be essential for ensuring that AI is developed and deployed responsibly. This will involve developing educational materials and outreach programs to educate the public about AI, as well as engaging in public dialogues to address the ethical and societal implications of this transformative technology. A well-informed public will be better equipped to participate in the ongoing discussion about the future of AI, and to ensure that this powerful technology is used to benefit society as a whole. The future of AI is not predetermined. It is shaped by the choices we make today. By fostering responsible innovation, promoting ethical development, and engaging in thoughtful public discourse, we can work towards a future where AI serves humanity's best interests. Shanahan, 2015. Key takeaways. Deep learning will continue to advance with more sophisticated architectures and specialized hardware. The pursuit of artificial general intelligence requires breakthroughs in knowledge representation and reasoning. Reinforcement learning applications will expand beyond games to real-world complex systems. Interdisciplinary convergence with fields like neuroscience and quantum computing creates new possibilities. Responsible AI development requires international collaboration and public engagement. Looking ahead, the future of AI in humanity. Learning objectives. Consider the long-term trajectory of human-AI coexistence. Evaluate different potential futures for AI development. Recognize the role of human agency in shaping AI's future. Identify critical decision points in AI governance and ethics. Develop a balanced perspective on both opportunities and challenges. The journey through the world of artificial intelligence has brought us to a pivotal point. Contemplating the future. We've examined the building blocks, witnessed the applications, and grappled with the ethical dilemmas. Now, it's time to look ahead, not with predictions of precise outcomes, but with a thoughtful consideration of possibilities and the roles we each play in shaping them. The trajectory of AI is not a straight line. It's a complex, interwoven tapestry of technological advancements, societal shifts, and ethical considerations. While we've seen the remarkable progress in specific AI tasks, from image recognition to natural language processing, the true frontier lies in the development of artificial general intelligence, AGI. AGI, unlike the narrow AI we currently possess, aspires to create systems with human-level cognitive abilities capable of learning, adapting, and solving problems across a wide range of domains. This is not merely an incremental improvement. It represents a paradigm shift, potentially altering the very fabric of human existence. The challenges are immense. Building AI systems that possess common sense reasoning, handle ambiguity effectively, and navigate the complexities of human emotions and social interactions. Success hinges on breakthroughs in areas like cognitive architectures, knowledge representation, and the integration of emotional intelligence. This requires a multidisciplinary approach, merging insights from computer science, neuroscience, psychology, and philosophy. The potential rewards are equally immense, with possibilities ranging from solving some of humanity's most pressing problems to unlocking new frontiers of scientific discovery. Beyond AGI, several other crucial areas warrant attention. One is the continuous evolution of machine learning algorithms. Reinforcement learning, for instance, is poised for significant expansion. While currently demonstrating impressive capabilities in games and robotics, its potential extends to far broader applications, from optimizing complex systems like traffic flow and energy grids to personalizing healthcare interventions. The challenge will be to develop reinforcement learning algorithms that are robust, adaptable, and safe, capable of handling uncertainty and unforeseen circumstances without unintended consequences. This necessitates rigorous testing and validation procedures, with safety and ethical considerations at the forefront of the design process. The fusion of AI with other technological fields promises remarkable advances. The synergy between AI and robotics is already transforming industries, with AI-powered robots assuming increasingly sophisticated roles in manufacturing, healthcare, and exploration. The future will likely see robots with enhanced dexterity, adaptability, and cognitive abilities, capable of operating in complex and unpredictable environments. Similarly, the convergence of AI and neuroscience holds immense potential for unlocking the mysteries of the human brain. By studying the brain's intricate architecture and computational processes, we can gain inspiration for creating more efficient, robust, and biologically plausible AI systems. The power of quantum computing could revolutionize AI, providing the computational horsepower to train significantly larger and more complex models than currently feasible. This could accelerate progress in fields like drug discovery, materials science, and fundamental scientific research. However, this advancement also necessitates thoughtful consideration of the ethical and societal implications of such enhanced computational power. The potential for both positive and negative consequences necessitate careful planning and responsible development strategies. Another critical element in the future of AI is explainable AI, XAI. As AI systems take on more significant roles in our lives, particularly in high-stakes domains such as healthcare and finance, the need for transparency and understanding of their decision-making processes becomes paramount. XAI aims to create AI models that are not only accurate but also interpretable, providing humans with insights into how they reach their conclusions. This is not merely a technical challenge, it's crucial for establishing trust, ensuring accountability, and mitigating potential biases. The development of XAI requires a multidisciplinary effort, integrating expertise in computer science, cognitive science, and human-computer interaction. Ethical considerations will remain at the forefront. As AI systems become more prevalent, addressing issues of bias, fairness, privacy, and accountability will be paramount. This requires a concerted effort to develop algorithms and techniques to mitigate bias in data and models, implement robust data privacy and security measures, and establish clear ethical guidelines for AI development and deployment. This is not solely the responsibility of technologists. It demands collaboration across disciplines, engaging ethicists, policymakers, legal experts, and the public in shaping the ethical frameworks that govern AI's development and use. The successful integration of AI into society depends on addressing several critical infrastructure needs. The training of advanced AI models requires access to vast datasets and substantial computational resources. Investing in robust data infrastructure, high-performance computing, and efficient data management techniques is crucial for fostering innovation and ensuring equitable access to these resources for both academic researchers and commercial developers. International collaboration is essential for responsible and equitable AI development. Sharing knowledge, resources, and best practices globally is vital for addressing the challenges and opportunities presented by AI on a global scale. International cooperation is also necessary for establishing global standards and guidelines for AI governance, ensuring that AI is used for the benefit of all humanity. Finally, education and public awareness are indispensable. Fostering a widespread understanding of AI's potential benefits and risks is crucial for ensuring responsible development and deployment. This requires developing educational materials, outreach programs, and public dialogues to address the ethical and societal implications of this transformative technology. An informed public is vital for participating in the ongoing conversation about the future of AI and shaping a future where this powerful technology serves humanity's best interests. The future of AI is not predetermined. It is a future we collectively create. The opportunities are boundless, but so are the challenges. By prioritizing ethical considerations, fostering collaboration, and engaging in thoughtful dialogue, we can strive towards a future where AI enhances human lives, advances scientific knowledge, and promotes a more just and equitable world. This is not a passive process. It requires active participation from all stakeholders, including researchers, policymakers, industry leaders, and the public. Let us embrace the responsibility and opportunity to shape a future where AI serves humanity, not the other way around. The journey continues, and the choices we make today will determine the destination. Key takeaways. The development of artificial general intelligence represents a potential paradigm shift for civilization. Multiple technological domains must converge to address humanity's most pressing challenges. Human agency and ethical frameworks will shape AI's future trajectory. International collaboration is essential for equitable and beneficial AI development. Education and public engagement are crucial for informed decision-making about AI's future.